Hi everybody, Chris Bryant here, and welcome to your free CCNP Switch Video Bootcamp, brought to you by the Bryant Advantage and our friends at Udemy. Online courses anytime, anywhere. First off, thanks for watching the introductory video, because no one ever wants to watch the introduction. They want to go straight into the course and get started. I understand that. I'm with you. We're just going to take a minute or two here to take a look at what you're going to get in this course, and we're going to start though with what you don't get. Don't worry, you're going to like this. First off, you don't get a bill. We all like that. It's a free course. You're not going to get a bill. Secondly, you're not going to get continual sales pitches, because the reason I mention this is that with any free course sign up or free email sign up, free sign up for anything, you can't help but to think, okay, what's the catch here? There is no catch here. I'm not going to insult your intelligence, though. I hope you'll check out my page, CCNP Switch and CCNP All-in-One courses here on Udemy after you watch this one. If you like it and you keep the videos, you don't sign up, no hard feelings. Maybe a few hard feelings. But, in all seriousness, I am not going to continually bug you about signing up for something throughout this course. What you are going to get throughout this course, though, is an hour and a half, actually a little over that, of lab-packed, world-class CCNP Switch Video Bootcamp instruction. And every demo I do here for you is going to be on a live Cisco switch, and there are plenty of them. Because especially when it comes to the hot standby routing protocol, HSRP, the topics, it's one of these things that when you read about it, it takes a while to sink in, if it ever does, just by reading it. But once you see it in action, it's like, oh, okay, it's not really complicated. HSRP isn't complicated, but you need the right demos to learn it, and you're going to find those right here. We're going to have demos of the fundamentals. We're going to take a look at the default. We're going to run a live lab on the active router election, and if you don't know what that is, you will about 90 minutes from now. And load balancing, kind of. You'll see what I'm talking about. HSRP load balancing isn't quite pure load balancing. You need to know why for your exam and for the real world, and you will see why in this free course. Also, the one HSRP topic that really trips people up, especially if you've just read about it, it's called interface tracking. And once you see it in action again, not only will you see that it's pretty straightforward stuff, you're also going to see how handy it can be in real-world networking. Because my courses aren't just for the exams. There are things you can apply in the real world as well. That's just HSRP. Then from there, it's on to Cisco switch security. We're going to review some port security fundamentals, because that's important stuff. You learn it in your CCNA, but I don't know if you got your CCNA 3 days ago or 3 years ago, so we want to make sure that these fundamentals are in your mind. We're also going to set some max address limits, do some sticky addressing, and go over a mode that's really misunderstood, but you will not misunderstand it once you're done with this course, and that is the error disabled recovery mode. That wraps up the introduction. I appreciate you taking a couple of minutes to watch it. I'm Chris Bryant, and on behalf of the Bryant Advantage and Udemy, welcome to this course. Let's get started. As we talk about hot standby routing protocol and see it in action, which is going to be very shortly, we've got several great HSRP labs for you in this section. I'm going to be referring to routers rather than saying switches or L3 switches or multi-layer switches, because the HSRP terminology itself does refer to active routers and standby routers. The theory and commands of HSRP, they run the same on a multi-layer switch as they do on a router, and in the lab we actually will be using multi-layer switches. Also, the icon that I'm using for multi-layer switches from here on out is slightly different. There's no SI in the middle. I just wanted to make sure that you saw both versions of that. Now, HSRP is defined in RFC 2281, and it's a Cisco proprietary router redundancy protocol. What we're doing is we're putting physical routers into an HSRP router group. One of the routers in the group is going to be selected as the active router. The others are going to be the standby routers. And it will not surprise you to learn at this point that the active router is going to handle the actual workload, and the standby routers, frankly, are going to sit there and they're going to stand by and watch the active router do all the work. Now, HSRP does ensure a high network time because we are routing IP traffic without reliance on a single router. Also, just a quick note here, the terms active and standby, they don't refer to the actual operational status of the routers. The backup router or the standby router, it doesn't go into some kind of suspended state. It's ready to go. It's just referring to its status in the HSRP group. Here's actually what we're doing with HSRP. Now, the actual IP and MAC addresses of the physical routers in the group, They're totally unknown to downstream devices. And in this case, that being our switch and a bunch of hosts connected to that switch, these devices are actually communicating with a router that does not exist. A pseudo router, a more popular term, a virtual router, and that's going to be created by the HSRP configuration. Now this virtual router is going to have its own MAC address, it's going to have an IP address that we assign it, and the downstream devices send data using those as the destination addresses. It's pretty cool stuff. So we're going to jump right in here with a lab. And in our first lab, we're going to have multi-layer switch 1, which has an interface VLAN 100 with an IP address of 172.16.23.1, and multi-layer switch 2, which also has an interface VLAN 100, address 172.16.23.2. Those are the two routers we're putting in the HSRP group. We're going to create a virtual router with this configuration with the IP address 172.16.23.12/24, and it's that address that will be used by all the hosts in VLAN 100 as the default gateway. So here's a diagram for you as well showing you those addresses, and let's go ahead and get started. Let's bring the live equipment up. Now I have pre-created, if you will, I've already created the interface VLAN 100 on both devices. And we'll just do a quick verification here. Here's show VLAN 100. It's up and up. There's the IP address 172.16.23.2. Now let's go over to multi-layer switch 1, MLS1. You can see, whoops, that should be 100. There we go. And interface VLAN 100 is up. Everything looks good there. 172.16.23.1/24 is the IP address. Just wanted to make sure I did show you VLAN 100 for number 2. Okay, so those again are the IP addresses that we're working with, the two devices, and we're going to create this virtual router at 172.16.23.12/24. We're going to start over on router 2. And these are interface level commands. Standby is the word we just keep coming back to. You are rarely, if ever, even going to type HSRP. But standby, I've got quite a few options here. Some we're going to look at in the next couple of labs. And the one we're going to look at right now is your only required one, IP. And that's enabling HSRP for IP version 4 and setting the virtual IP address, which is a good idea. So without that, we're kind of stuck. So let's see what we need before that, though. We actually need a group number, and I'm going to put 5 for ours. And I'm going to then enable HSRP for IP version 4 with IP. Then I'm putting my virtual address, 172.16.23.12. You could make it a secondary virtual IP address. I'm not that much on secondary addresses, and that's not something we're going to cover in the labs anyway. It's beyond the scope of the exam. And we're just going to stop right there and see if anything happens. We'll get a little console message, and let's run show standby. We're going to be running this one a lot. And state is listen at the very top, and I'm going to show you all the states. We'll discuss those and look at the order of them. But right now it's just listening for something. And let's go ahead and finish the config over on MLS1. Standby 5, IP 172.16.23.12. And that's it. Now let's go back over to switch 2. This may take a minute or two to finish cooking, so to speak. As you can see, state is active. It's showing a couple of state changes. We see the virtual IP address. There's an active virtual MAC address as well. We didn't enter that, but there is one. And let's see. Standby router still unknown. So let's give that a moment to cook, so to speak, and let them talk to each other. And now you can see it's changed from standby router is unknown to a few seconds later, standby router is 172.16.23.1, priority 100. And it looks like things might have settled right there. So you can see we had another state change. That's been about 53 seconds. This is the active router. Active router is local. Standby router is 172.16.23.1, which is router 1. So let's just go ahead and verify that. Trust but verify. Show standby. Group 5, you can see that one state change was about 44 seconds ago. The state is standby. There's the same virtual IP MAC address. We expect that. There's the same virtual MAC address. Something called preemption is disabled. You see the active router 172.16.23.2. We see its priority, and there's the standby router is local and the priority of the local router. So far so good. That's exactly what we expected to see. What we saw on switch 1 verified what we saw on switch 2. And let's go down. We've seen all this on the board. One thing I did want to show you here, you cannot assign an IP address from the multi-layer switch as the IP address for the virtual router. And here on this line I tried that. Standby 5 IP 172.16.23.1. The router told me address cannot equal interface IP address. I'm the one who added, so don't try it. Cisco doesn't have that much of a sense of humor, but I do. So let's go down the roll here, down the line. We'll start with MLS 2. And let's go down this information one more time, because you're going to go to show standby. This is your #1 verification command. It's your #1 troubleshooting command. You're going to keep coming back to this, so we really need to know the information we can expect to find. First off, here's your VLAN number, and it's in group 5. State is active, and again, we'll come back to those states here shortly. We've had 2 state changes, and the last state change was 2.5 minutes ago. If you see these continually changing in what you think should be a stable configuration, then that's a tip-off that it's not a stable configuration. You've got something wrong. There's no reason for HSRP state changes to be a regular thing, like every couple of minutes. Definitely shouldn't happen. There's our virtual IP address for the router itself, the virtual router. Again, there's that MAC address. And you notice V1 default here. Version 2, I believe, is for IP version 6, and that is way beyond the scope of the NP switch exam as far as HSRP goes. So we've got our hello time here of 3 seconds and a hold time of 10 seconds. Those must be the defaults because we didn't send them. It even tells you when the next hello will be sent, down to the thousandth of a second. That's pretty exact. Preemption, again, is disabled. We'll talk about that shortly, I have a feeling. Active router is local. There's our standby router 23.1. Even tells you what the priority is. Tells you the priority of the local device. And then finally the group name, not something we get into a lot, but that is the default name, and you'll notice the group number is at the end of the default name. So a treasure trove of HSRP information in there. Tells you the states, the IP addresses of the standby, tells you whether you're the active or not. A lot of great stuff. If we go back over to switch 1, and let's get a fresh show standby there. We have the same fields, just of course the information is a little bit different. You can see the last state change was almost 4 minutes ago. State is standby. There's that virtual IP. Let's talk about that virtual MAC address, though. We know where the IP address came from. We're the ones that entered it. That's the one required command you have. Well, where did that MAC address come from? This is derived from the well-known MAC address that's reserved for HSRP. So most of that address was predetermined. Almost all of it, actually, 0000C 07 AC, all of that is predetermined. The 05 here, that's the only part that isn't predetermined. Now that is the group number, and I know you're saying, hey, no kidding, but it's the group number in hex. So you need to brush up on your hexadecimal before you take the switch exam, because that could creep in. And of course, if you saw AC0A here, the group number would actually be 10. If you didn't know that, you do need to brush up on your hex. Nothing wrong with that. Just a quick story here. It was a long time before I even started running courses like this. And it had been a very, very, very long time since I saw hex on any certification exam, anything. And the day I took the CCIE lab, there was some hex at the very beginning of it. And if you couldn't solve this, then you couldn't do the rest of the lab. so I had to wait until some brain cells came back there after a few minutes. There was a moment of panic, but you don't want that panic on your exam. So just take a few minutes to brush up on your hacks before you take the switch exam, and you will be fine. But that is exactly where the MAC address comes from. And here's our current network. MLS2 is the active switch, MLS1 is the standby switch, our virtual router 172.16.23.12. That also concludes our first lab. What we're going to do next is talk about that election process and how to change the results if we're not real crazy about it. We'll do that in a lab at the beginning of the very next video. See you there. One quick addition to that last lab before we move on to the router election. One thing you should do after you've got your virtual router up and running and everything looks good on your multi-layer switches is to go to one of your hosts and make sure they can ping that new virtual router. So I just went out to host 3, which was already in VLAN 100, and pinged 172.16.23.12 from there. No problem at all, and the pings came right back. So let's talk about this election for a few minutes, and then we're going to jump in the lab really quick and look at changing the results of this election. The priority, that HSRP priority, it's the first value considered in the election. Now the priority is 100 by default. We saw that on both routers. And just a quick reminder of where to find that. Of course, you know it's in show standby. Everything's in show standby. But your local router is going to be right down here, your priority. Priority 100. Notice it says default 100. I think that word in front of the number there in the paren is going to change, so we want to watch that. But there's the priority. So everything looks fine there, except should there be a tie? Well, there always will be a tie if we leave the routers at their defaults. Theory holds that the router with the highest IP address wins the election. Now, multi-layer switch 2 won the election in our first lab and had the highest IP address on the SVI. So the theory holds true, and that could be any interface. But the problem there is that doesn't always work, and I'm speaking real world here. Always, always, always verify your active router. I know I say to verify everything, but you really want to verify this because I've seen routers with lower IP addresses win that election, and the priorities are the same and everything else is the same, so you just want to verify that. For your exam, we're going to hold to the theory that the highest IP address wins the election. So let's go ahead and make multi-layer switch 1 the active router, because we know in the real world, it's just like our root switch elections. We don't always want to leave that up to the MAC address. So maybe I've got one particular workhorse switch here and another one that's not so much. So I want to make the first switch the multi-layer switch. So let's just go into inner VLAN 100, interface VLAN 100, standby 5, and we just use the priority option. And your priority is 0 through 255. So I'm going to go double or nothing here and double the default priority. And to get a console message, but it's just the old configured from console by console message. We're pretty used to seeing that one. We don't see anything about a state change though. And this is good and bad on MLS1. The good part of it is that the priority change did take effect. There it is. Priority 200, configure 200. Whenever we see configured, we know that somebody hard-coded that particular priority. The bad news is that there wasn't a state change. We could see here first off state is standby. So router 1, multi-layer switch 1 didn't take over as the active. And the last state change was 9.5 minutes ago. So, not so much here. What happened? Well, the deal is with HSRP that either, in this case, multi-layer switch 2 has to disappear for 1 to take over in its absence. We don't really want to do that. We don't want to reload the switch. What we'll do much more commonly is use the preemption option. Okay, preemption is disabled by default in HSRP. And here's the preempt option. Overthrow lower priority active router. Sounds kind of violent. I don't overthrow. That's pretty violent. But that's the only option. That's the one we're going to use. When you enable preemption, then a router can take over as the active if it has a higher priority than the current active. Because right now, switch 1 has a priority of 200. Switch 2's got a priority of 100, but it's keeping its role as the active. Let's see what happens when we enable preemption. And you just put preempt, and that's it. And in a very short period of time, and I'll move this over so you can see it, I know that timestamp is long, the state change, HSRP 5 state change, VLAN 100, Group 5 state standby to active. So it sounds like it did exactly what we wanted it to do, and it did, because now this is the active router. This is the active router, 2 state changes. It just changed 17 seconds ago. All the IP address and hello time and all that stuff stays the same, but preemption is enabled. Active router is local, and here's the standby router 23.2 with a priority of 100. Remember, the priority it mentions here is the priority of the local router. So it did exactly what we wanted it to do, but that's the key. It's not enough just to go in there after the election and raise the priority of the switch you want to be the active router. That's not enough. You've either got to reload the active router, which we generally don't want to do, or just enable preemption. There is one option here too. I'm going to show you this. There are some options there for preempt. Because those of you who've seen, and you might still see an iOS version where this happens, you used to be able to set preempt at the end of the priority command. And I don't think you can do that anymore, period, but you might bump into an older iOS that does let you do that. I do want to show you these options, though. You can delay the preemption. So if you want to say, okay, I want to wait 10 seconds before preempting, or I want to delay it until after a reload, then you can do that. You might run into specialized situations where you want to do that. The sync option, do not concern yourself with that right now. But let's look at minimum. And it's just the number of seconds for minimum delay. So, again, you might run into some specialized situations out there in real world networking, but generally for lab work, it's good. They're good options to know, please don't get me wrong. But generally, when I preempt, I want to go ahead and just do it right then and there. That's really it. So that is it for this particular lab. We are going to head to the next video now. We're going to talk about those state changes. We've seen a couple of those in action. We've seen active, standby, certainly. We've seen active and standby in all of our labs. But I want you to know about the stages that lead up to those, and we'll talk about that on the very next video. Before we start on our next lab, let's go over these HSRP states. We've seen a couple of them, especially standby and active, but let's go through them in order. Disabled is officially the first HSRP port state. It's very similar to STP in that you won't actually see it mentioned. You won't see HSRP disabled in a console message, but it is the first official port state. Now, initial or init, the interface enters this state when you first enable HSRP on it. HSRP isn't actually running at this point. The only other time I've ever seen that, it's in a lab environment, thankfully. If you went in, let's say right now on one of the routers and deleted interface VLAN 100, you would see the HSRP state go from active or standby, depending on which one you're on. If you're on the active, it would go from active to init, and then it would just sit there, which is not what we want. Now listen, that's the next state, and that's when the router knows the virtual router's IP address, but it is not yet the primary or a standby, and it's listening for hello packets from those routers. In speak state, the router is now speaking, it is sending hello messages, and it's participating in the election of the primary and standby. Standby, we've seen that a couple of times. The router is a candidate to become the active. It continues to send hello packets, and then finally active, the router is now forwarding packets sent to that group's virtual IP address. Speaking of forwarding packets sent to the group's virtual IP address, let's talk about load balancing here for a bit and see it in action as well. Now, I have reset things from the previous lab as far as the priorities go, so right now everything is back at the default, and switch 2 is the active router for our group. Switch 1, of course, is just standing there, standing by, and watching MLS2 do all the work. Now, assuming that we had 60 hosts in VLAN 100, that means that right now, switch 2 is handling the traffic for 60 hosts, and our other multi-layer switch, switch 1 is just standing by, watching. We would like to do a little bit of balancing here. Now, this balancing is going to be a little bit different because it does require a little bit of cooperation from the hosts. And we'll talk about that after we get the switches up and running, because I guess tricking may be a harsh way to put it, but we're kind of tricking HSRP a little bit here as far as I'm concerned, because what we're going to do is create another group. Right now, HSRP Group 5, it has Switch 2 as the active router, and that group is using 172.16.23.12 to represent its virtual router. What we're going to do now is create Group 10 with the same two routers. There's nothing illegal about that yet. We'll find out in a minute, I guess. Making sure that one is the active, Switch 1 is the active, and that group will use another address, 172.16.23.21, for its virtual router. So this is what we want to end up with, in essence. We want to split this load. It's not pure load balancing, of course, because we could have some hosts sending a lot more traffic. But the thing is, it's better than what we had. So in the end, we want Switch 2 to remain the active for Group 5, but be the standby for Group 10. We want the inverse, really, for Switch 1. We want Switch 1 to be the active for Group 10, but the standby for Group 5. Okay, so we're already halfway there because we know that Switch 2 is the active for Group 5. And let me move that up. And we can just verify right here, of course, before we start a lab. Show standby, VLAN 100, Group 5. State is active. So let's go ahead and create another group. And we're going to start that over on Switch 1. And we just go right back under VLAN 100. But this time, of course, we're using standby 10. That's our new group. 172.16.23.21. That's going to be the IP of the virtual. Standby 10. We're going to go ahead and double the priority again. And we're going to let this one preempt. And that's all we need there. We need even less over on MLS2. Move that. And let's try that again. VLAN 100. Just came right back. Standby 10. IP 172.16.23.21. And that's it. So we're going to let that cook for a minute here and see how it goes. Actually, let's go over to 1 and see what it's saying already with show standby. And when you run show standby there by itself, it's going to give you the info on all the groups. And you can see that it's still the standby for Group 5. But Switch 1 is now the active for Group 10. Now it says standby router is unknown, so it's not done yet. But let's go ahead and run it again now. And you can see that we get exactly what we wanted. Group 10, Switch 1 is active. There's the IP address. There's the MAC address. Notice the 0A at the end of it. Remember I told you a Group 10 would be 0A there because it's hex. There you go. Preemption's enabled. Active router is local. Standby router is 172.16.23.2. So that's exactly what we wanted. Let's go over to Switch 2 just for fun. And we can see that in Group 5, this switch is the active router. Active router is local. Standby is 23.1. And for Group 10, the story is a little bit different. Group 10. Let's try that again. Group 10. And we've got active router is switch 1, 23.1. And the standby router is local. So that's all there is to load balancing. Again, it's not absolutely perfect, but it's really, really good. And here is essentially what we have now. We're going to test this in a moment. Because remember I said something about the hosts? We're not quite done with our load balancing until we give about half of our hosts one of the virtual router IP addresses for a default gateway. Then we give the other half of the hosts the other virtual router's IP address as a default gateway. That's the way you got to split it up. So you can see here, just using two hosts, we've got host 2 with its default gateway pointing to 172.16.23.21, and that's the path it's going to take. And then host 3 has a different default gateway. It has the other virtual router's IP address 23.12 set as the default. So let's go ahead and send some pings there and just make absolutely sure. Let's see if we can get that up there to stay this time. And we've got 2. We're going to head out to router 2. and do a 172.16.23.21. No problem there with it pinging its virtual, its default gateway, which is a virtual router IP address. Now host 3, we're going to ping the other one. And all is well. So that's really the key, is that you just have to remember that you're not quite done with your load balancing when you get that second virtual router up and running. You are done with it when you go to your hosts and you change some of their default gateways, half of them pointing to one, half of them pointing to another, and you're all set. That is it for load balancing. Now next up, we've got something called interface tracking. It is an absolutely fantastic feature you're very liable to run into in the real world, and you're definitely going to see it on your exam. So let's head to the next video and we'll run that lab. HSRP interface tracking. This is a great little feature, and what it does, it enables HSRP to monitor an interface that you and I as the network admins specify, and the status of that interface will dynamically change the HSRP priority for a specified router for better or for worse. And let's find out which one that's going to be. When that tracked interface's line protocol goes down, the HSRP priority of the router is decremented. Of course, a fancy way of saying it goes down. Now, this can lead to another HSRP router in the group becoming the active, but that other router must have preemption enabled. Now in this diagram, I have not indicated or not put the virtual router in there. We know it's in there, and we're actually going to configure that because I've got these IP addresses, the interface VLAN 100, but that's it. So we're doing everything else from scratch in this lab. And what we're going to do is set MLS 2 up with a priority of 105. It should, of course, become the active because it's going to have a higher priority than 1, which we're going to leave at the default priority of 100. Well, as a result, then 2 will handle all the traffic sent to the server behind MLS 1 and 2 here. You can tell it's a very important server because I put a giant bag of money next to it. Well, there's nothing really wrong with that, but there is a single point of failure, and it might not be the one you're thinking about that could cause some trouble. And again, the IP addresses shown for the multi-layer switches in this lab are for their SVI for interface VLAN 100. The problem here is that if Fast Ethernet 3 on switch 2 fails, the hosts in VLAN 100 can't get to the money bag server or whatever server we've got back there. But by default, that Fast Ethernet port going down is not going to affect HSRP in any way. It's not going to bother it at all. So what we're going to do is change that default a little bit and put some tracking on there. First, we're going to go ahead with a configuration, but first, I've got something here to show you. On switch 2, I've got show interface Fast Ethernet 3. Save yourself a lot of time and agony when you're configuring HSRP interface tracking. Always check the status of the interface before you even start. Because if there's something wrong with this interface and you don't realize it, then you're going to get some comeback or some feedback from your show commands in HSRP that you're not expecting. And you end up troubleshooting your HSRP config because that's the last thing you did when the actual problem was the interface you were tracking was down already. Not that that ever happened to me. I just heard it, from a guy, so I'm sharing it with you. Okay, I'm lying. It did happen to me. Not here, but I did learn that lesson the hard way. Let's go ahead and get started with our basic config. We'll go with standby group 1 this time. 12. I try to put 12 in there. 1623.12. And we're going to set the priority to 105 there, and that's going to be it. And that's it. So right now on switch 2, use the standby IP command to enable HSRP, create our virtual router. Then I set it with a priority of 105, interface VLAN 100. I enabled HSRP, same address, of course, same virtual router, and enabled preemption. So let's go forward. Let's take a look at 6s here and just make sure. At switch 2, and you can see you've got a couple things, all of which we really expect to see. There's VLAN 100 group 1 state is active, preemption disabled by default, active router is the local, standby router is 23.1, and there's priority 105, and of course it says configured 105 because we put that in there. Let's go back to switch 1 for a moment. Run the exact same command and we see what we expect to see, that the state is standby, preemption is enabled, active router is 23.2, there's that router's priority, our standby router is the one we're on, and our priority is 100, and it even says default 100, which of course your switch and then your T-shoot exams are not going to tell you, so that's another great value to have absolutely memorized. We got another one coming up as well. So let's go ahead and start with our interface tracking. And I'm going to hop over to switch 2 to get that done. Let me show you this command. Interface VLAN 100, standby 1, and what we're doing here is tracking. They call it priority tracking. That's fine with me. I don't care what you call it, as long as you know how to do it. So we're going to use track here, and then we got a huge list of interface types, plus a tracked object number. We're not getting into the numbers here in your CCNP studies. We're going to stick with the interfaces. So we're going to put fast Ethernet, maybe 0/3, and we have a decrement value of 1 through 255, but we can also just enter the command as it is. So what could be that decrement value? That default is 10. That's another really good value to have memorized. So everything being equal right now with what we've put in, switch 2 has a priority of 105, switch 1 a priority of 100. So if we decrement switch 2 by 10 and we have preemption enabled on the router we want to take over in case this interface goes down, then we should be set. So let's go ahead and go with that default. Then we're going to go to that interface and we're going to bring the line protocol down because we're going to shut the interface. And we get all kinds of messages right away. One that we haven't seen before, notice the top line, the top log message, I'd say the console message, tracking 5 state, 1 interface fast 03, line protocol up to down. Then all kinds of other things happen. Right after that tracking message, there's the one we hadn't seen before. Here's your HSRP state change message. We went from active to speak immediately. Then we get the usual messages we expect to see when we shut an interface down, change state to administratively down, line protocol change state to down, and this all happened in about a 3-second period. Then 12 seconds after we shut that interface down, the local interface has gone from speak to standby, the local switch I should say. So let's do show standby and we'll see the aftermath of what we did. You can see that priority 95 configured 105, so something made it go down, and certainly we know what it is. And here it is, right in show standby. Track interface fast Ethernet 0/3, state is now down, and it decremented by 10, and we see also the state is standby. Let's go over to switch 1. Pretty much know what we're going to see here, but we're going to run it anyway. And you can see now it is the active router is local, standby router is 23.2, which is .2, and it even shows you now that switch 2's priority is 95. So that's pretty cool. Now, the obvious question is, what do we have to do as network admins when switch 2's interface comes back up? You know, is the cutover going to happen immediately? Do we have to do something else? What do we got to do? Well, there's only one way to find out, by golly, and let's do that. We're going to reopen that interface. And let's see what our console messages are this time around. Okay, we've got a tracking state message in there. So the interface went down physically right after we did that with a no shut. And then here's your tracking state. It's already detected the line protocol's gone up. It even gives you the direction. Can't beat that. Down to up. So then we get the usual interface change state to up. Then the line protocol went up. What aren't we seeing here? We aren't seeing a message about this router becoming the active. It didn't even change any states. It just noticed, hey, I'm tracking this interface and it's gone up. But nothing else happened. Is that a problem with the log messages, you think? Console messages? Let's take a look. Well, the active router is still 23.1 and we're still the standby router even though the priority went up correctly. So tracking seems to be working fine. And here it even says track interface fast Ethernet 0/3, state is up, decrement is 10. What is going on here? Why isn't switch 2 taking over as the active? The answer is right in front of you. Preemption disabled. If we want this router to take back over as the active when that interface that we're tracking comes back up, and we probably do, then we have to enable preemption here as well. Always watch preemption. There's a reason I'm hitting you over the head with it. And I'm not going to put anything else in, and you can see immediately we get a state change from standby to active, and now everything that we wanted to have happen, switch 2 going back to being the active, seems to have happened. Yep, there you go. So active router is local, standby is 23.1, priority 105, the tracking information is correct. There is the key right there, preemption enabled. That is the key. If we want that router to become the active one again once the interface is fixed, and again we probably do or we wouldn't have made it the active in the first place, then we've got to enable preemption. Before we move to the next lab, I know another question that's likely on your mind now. It's like, well, should I just always enable preemption? You know, when I'm doing HSRP, should I always enable preemption? Of course, there is no one-size-fits-all answer to that question. Some people think it's a little bit of a security hole. I'm not really on that side. But it just depends on what your deployment is. It's not something I would just automatically put every single time on every single router, because of course you could have multiple switches in there in your group and you say, well, here's one I really don't want to become the active. So it's not something I would just do blindly, but I would just analyze your network, take a look at it. You're a CCNP, you look at it and say, here's where we need it and here's where we don't. But I would not just blindly enable it every time. On your exam and in your lab, and on job interview questions and in the workplace, the first thing I look for when I'm not seeing the kickover that I expect to see with tracking is making sure preemption is enabled on the switches that need it. So let's see, we're hitting about 11.5 minutes on this video. We're going to go ahead to another video, and I am going to reset the switches. We're going to do another tracking lab, and then I've got some other great labs for you right after that. So I'll see you in the next video. I am going to call an audible here, my friends, and we are going to just pick up exactly where the last video left off. And you can see I've still got show standby up there. And we know for switch 2, we know that both switches have preemption enabled at this point. We know the priority is 105 on switch 2 and 100, the default, on switch 1. Let's see what happens, though, when that default decrement isn't enough. We know that's 10. We've got to have that memorized. But let's set switch 2's priority for this group to 150. And we'll verify that. I was waiting for a message. There we go. Show standby. We see priority 150, configured 150 right here at the bottom. So everything is beautiful. Now, I know that you know right now what is not going to happen if Fast Ethernet 3 gets closed again, but let's do it anyway just to see what the deal is, what exactly is going to happen. And we'll shut her down. And we immediately get the tracking state message, you know, hey, I'm tracking this interface, Fast Ethernet 3, the line protocol has gone from up to down. Then we get the usual messages, the system console message, the port's gone administratively down, and then of course if the physical state is down, we know the line protocol doesn't have long to go, but nothing else is happening. We're not seeing any state changes, router 1, switch 1 doesn't seem to have taken over. So what's the problem? Well, we know it's that decrement. Let's go ahead and run show standby. And we can see that the decrement took place. You know, there's priority 140 configured 150. Well, if we're using the default decrement, though, that's 10. And 150 minus 10 is definitely not lower than 100, and that's what we need for router 1 to take over. So in this case, if the priority is set to 150, the decrement needs to be at least 51, right? So let's go ahead and configure that. And we're going to go under VLAN 100. Let's see if we can do it this way with the up arrow. tracking command. How far back do we go? There we go. So now we're going to use that decrement value we saw earlier, because we can set this from 1 to 255. It's just that we took the default of 10 earlier. So what we'll do here is set it to 51. And it does actually take place immediately because, of course, the interface is still shut down. So all we did just now was tell the router, hey, if that interface, and I know I keep going back and forth router to switch with HSRP, if that interface goes down, I don't want you to subtract 10 from the priority of this device. I want you to subtract 51. So that's the difference right now, and you can see it took effect immediately. And we'll run show standby. And we see right here at the bottom, here's priority 99, configured 150, track interface, fast Ethernet 3, the state is down, and the decrement is 51. Does this happen in the real world a lot? Not a ton. It's a good thing to know for your exams, job interviews, that kind of thing, practice exams. Most of the time, you're just going to leave your HSRP devices at the default, but you may run into situations where you need to change the decrement a little bit along with the priority. So let's go ahead and open that interface back up. And since we still have preemption on switch 2, I believe, there's interface changed to down. Yep. There's again the tracking state message. The line protocol on that interface has gone from down to up. State goes from standby to active. We run show standby anyway because we always trust, but we always verify. Well, we mostly trust. We mostly trust, but we do always verify. And you can see again, active router is local. Standby router is the other switch. So we are in fantastic shape there. That is how you change the default decrement in interface tracking. It is an important skill to have. So definitely something you want to watch out for in your troubleshooting and on exam day. Speaking of important things to know how to do, the next section is a little bit of this or that, as my nephew calls it. It's a little bit of this and that with HSRP. There are little things you need to be able to change that aren't going to be huge labs by themselves. So I'm going to put them all in one video, and you'll see how to change, and we can change the MAC address if we wanted to, but a couple of other things that you might want to change in here that just take one command. So we will wrap up HSRP on the very next video. See you there. Time to do a little this and that with HSRP. A couple of things I want to show you, and the first one is changing the timers. Frankly, you can leave the HSRP timers alone, and I don't think the overhead is terrible. But if you really need to change these or need to change them on the exam, you certainly need to know how. What I've done since the last video is just I took all the old configs off, and the only thing I've put back on is the standby 5 IP command. That's it. So we're looking at all defaults here. And on switch 1, we're looking at a hello time of 3 seconds and a hold time of 10 seconds. And we can change that. Let's see how. I bet you can guess where we start by this point, certainly. And we go standby 5, and we're going to use the timers option for hello and hold timers. Now, we can set the hello interval in seconds from 1 to 254. You can specify the hello interval in milliseconds. That's pretty retentive, and you're talking to a retentive guy. That's pretty deep. You really don't need to go that far with it to do it in milliseconds. What I would do here, let's say we want to double that, and then you've got to enter a hold time, even if you're going to keep the 10-second hold time. Notice that we do not have a CR here, so you've got to put it there. We'll go with 15 seconds here, just pulling a rabbit out of my hat. So standby 5, timer 6:15 means we've reset our timers to 6 seconds for the hello time and 15 seconds for the hold time. Now, you'll note the only message we received from the console was configured from console by console. We didn't get any HSRP related messages. And you might have thought we'd get one because I haven't changed the timers on switch 2. They're at the default. Timers don't have to match between routers in an HSRP group. I strongly recommend, and Cisco also recommends, that you do keep them the same on all your routers. So the thing is, you don't want to get it out of whack to where you've got a hold time somewhere of 10 seconds, the default, and on another router you set your hello timers to 12 seconds. Then you're going to end up with some issues. So I would just keep my timers consistent. Changing them, not a big deal. Now you know how. Let's take a look at authentication. A couple of options here I want to show you. And the first one, Well, let's go ahead and bring up that standby 5. And we've got authentication right here at the top. And I'm not even going to show you plain text authentication, because if you're using plain text authentication, shame on you. You really should be using MD5, and I realize that Cisco router MD5, by their own admission, is not the hardest thing in the world to crack, but it beats the over-the-shoulder network attack where somebody just looks over your shoulder, sees what your password is, and comes back later. So we're going to use the MD5 option here, not MD6, and we've got key chain and key string. And when you're looking at these two right next to each other and maybe you haven't used them, it's like, well, what's the difference? Well, we're going to use a key string first. And a key string is just a fancy way of saying I'm going to enter a password. Maybe. There we go. And we're just going to put the password in here. We're not going to paste anything. We're not going to use that 0 or 7. And what we're going to do is just put CCNP right there with no null space. Watch that. And that's it. So now you'll notice we're getting a bad authentication from 172.16.23.2. That, of course, is because we haven't gone over there and set authentication up yet. So that can happen. What I did want to show you while we're over here was something in the config. Now I set this to MD5 authentication, but is that password of CCNP going to show up in the config itself? Could have done a filter all the way to the bottom, but that's okay. Yeah, it's right there under Interface VLAN 100. It's just sitting there. Now, what can I do to encrypt that? That's your first clue. There's a service I could use here. I love it when I remember to put the hyphen in. Service password encryption. That's an old CCNA friend of ours. And I'm going to use that right there. And you can see now I've got a key string with a lot of numbers that someone cannot look over my shoulder and say, oh, okay, the password is 03277822536. Doesn't work that way. Now let's go over to router 2 and set up authentication here. And it's just standby, then the group number, then authentication. And we're going to use MD5, of course, and a key string. And then CCNP, and then we will wait, and hopefully everything will be beautiful. See, state is active. Last state change was 9:13 ago, so let's keep that rolling. You see right here in the middle, authentication MD5, and it says you're running a key string, but it doesn't say which one. And this can take a little bit of time. Active router is local, so we've gone back to where we were, where active router is local, standby is .1. And we'll just go over to that one and make absolutely sure. And there you go. So that's authentication right there. Now that's with a key string. A key chain, I'm going to show you how to configure one of these in case you haven't seen one before. And it's a little tricky at first. So you go key chain. Might be trickier than I thought. There we go. Keychain without the hyphen in the middle. So I love this. You know, it's keychain name here with the hyphen. When you get to the command, it's gone. So I do that quite often. Keychain, then it's what you're calling your chain. Your chain can really be thought of, you know, the way I've always remembered it, like a key ring. You got a key ring, and you've got a key to your house, and you've got a key to your car, and you've got a key to your office. Maybe some other keys you don't want to tell anybody about, and that's all cool with me. But the thing is, that's what a keychain really is. It's a series of keys. And what you do here, you create one. And what I would do here is just create one with one password right now. That's what I'm going to do. So let's just put I'm going to call it HSRP. Just so I can look at it later and say, oh, okay, that's what it was. Then you have to give it a key. Your first key is given a key number. So I'm just going to say, okay, key 1 is CCNP. Now, I do have some other options here. You see accept lifetime and send lifetime. That's another reason you get into keychains, because I know, especially when you start using, it's like, man, this is ridiculously complicated. Why don't I just use a password and I'll change the password if I ever want to? You can do that, but if you want to for other features, so you're going to use keychains for security features, you're going to use them, I believe, over in the routing course, the NP routing course as well, for other features. And what you'll want to do sometimes is say, okay, this key is good from this Monday to this Thursday, and then that's it. So, or you could do the send lifetime, how often you can, the valid range when you can be sent. So it really can be helpful when time gets involved. If this is a one-time only password, I'm probably going to go ahead and use the string myself. But what I will do instead is set key string, and here's where the actual password is. And that's it. And if I want to create another key string while I'm here, I would call it key 2 and go forward from there. Again, I know this looks a lot more complicated than just setting a password. And again, for authentication for something like this, for HSRP, personally, I'm probably just going to go ahead and set a simple key string. But for other features that you're going to run into in the future, especially if they're time related, these keychains really, really come in handy. Then what you would need to do is learn how to spell exit. Then what you would need to do is go under here. If you were using that keychain, MD5 keychain, and then you give it the word name of the key chain, not the key string that you put in. So here I wouldn't put CCNP. What I would put here would be HSRP, the name of the keychain I just created. Again, first time you use keychains, you'll trip over it a little bit. That's no big deal. It's just part of the learning process, but it will come to you. And again, just going to mention it one more time. For time-related passwords, this is the way to go with keychains. That wraps up our time with HSRP, and you are, as you move to the next video, about to have the biggest case of deja vu in the history of network certification training, because the next protocol we look at, VRRP, is going to look so much and feel so much like HSRP that you're going to wonder why we're even looking at it. But there are important reasons. First off, there are some important differences. Secondly, it is going to be on the test. And third, VRRP is our industry standard protocol, where HSRP is Cisco proprietary. So go ahead and take a quick break. I'll see you in the next video, and we'll start with the Virtual Router Redundancy Protocol, VRRP. We're going to start our look at Cisco switch security with port security, and it's a feature that you learned about in your CCNA studies. We're going to make sure that it's easy points for you on exam day as well, with several different labs where we're looking at almost really every option of port security, because there aren't that many options. And on top of that, the overall operation of port security is very simple. It's what we have right on the board. You got frames coming in on a port, and the switch asks itself, is this frame from a trusted source? That's it. That's port security. Now, of course, we have a few options we got to know about, but this is what's going on. And of course, the decision there is, well, how do we decide if it's from a trusted source or not? Well, what we're going to have is a table of secure MAC addresses. And it could just have one secure MAC address in it. It's on a per port level. So one port will have, some secure MAC addresses, another port may have others. And if frames with non-secure source MAC addresses come in on that port, the port takes action ranging from shutting down entirely to just letting you and I know about it. We're going to see all of this in action. We're going to see the tables I was talking about. We're going to set some static MAC addresses, see some dynamic ones, the whole bit. Now, before we do any of that, we have to enable port security, and we're going to do that at the port level with the switch port security command. And we're just going to fool around here with a couple of commands before we actually get into some labs. With switch port security, we have a couple of options there: aging, MAC address, maximum, and violation. We're going to see all of those in action. But switch port security by itself is also a legal command. And what it does is actually enables this function or feature on the port. So then, of course, you press enter. Oh, and you get rejected. Well, you get rejected here because it says fast Ethernet 0/1 is a dynamic port. Okay, what do you want for my life? What's that got to do with it? The problem here is that you can only enable port security on a port that has absolutely no chance of becoming a trunk. Not that it's trunking now, that it can't possibly become a trunk port in the future. And we know what that means. We got to make it an access port. Because we could look at the switch, and I believe right now we don't even have any trunks. We have 0 trunks on the switch, but I still have to make that port an access port. So let's go ahead and make that happen. Let's try that again. Switch port, and boy, yeah, that's skipping right there. There we go. Sorry about that. And the VLAN doesn't exist, which is always nice enough to create it for me. And let's try switch port security again now. And we are enabled. You're not going to get a confirm message that says you just enabled port security, but we can confirm it with one of several show commands. A lot of people spend all their time with show port security, and there's nothing wrong with that command, but there are definitely some other show port security options I'll show you in the labs ahead. Right now, though, let's go with show port security. And going from left to right here, secure port, then it's got the number of maximum secure addresses, then the current secure addresses, then security violation and security action. And the key here is, really want to point this out, a lot of people, I should say a lot of people, some people, their eyes go straight to that shutdown, and they say, oh, well, you know, the port is shut down. The port is not shut down. Here, the situation is, this command is just telling you what the security action will be if there is a security violation. But we haven't had any security violations, so far we're good to go. I have a feeling that just might change in the labs ahead, but we're going to stick with that for right now. So let's see, we've got show port security. I'll go ahead and show you a couple of others here, a little advanced work. Here's show port security address. And we can see that it shows you what VLAN it is, the MAC address, the type, the ports, and remaining age in minutes. And we have a dash there, which means probably it's been disabled. Also note that the bottom of both of the outputs, show port security address and show port security, total addresses in system excluding 1 MAC per port, and then max addresses limit in system excluding 1 MAC per port, 6,144. That's a lot of secure addresses. So we're going to come back and see these tables in action as we proceed through some labs. Just want to give you a little feel for the show commands right now. And we have one more I want to show you. It's show port security interface, followed then of course by the interface type. And going from top to bottom, you can see port security is enabled, port status secure and up, which is a great combination. Violation mode is shut down. That is the default. You likely remember that from your NA studies. Aging time of 0 minutes, absolute. Aging type, absolute. We'll go over those when we change the aging types. Maximum MAC addresses of 1, total MAC addresses of 1. Configured MAC addresses then is 0. Sticky MAC addresses, we've got a lot of address types here, 0. What I like about this command, it shows you the last source MAC address that came in and the VLAN number of it. That's pretty cool. And it also shows you the security violation count. Again, just want to show you those now, and we'll see them in action during our labs as well. Let's go ahead, go back to the port, switch port security, and look at our options here. And we're actually going to start with maximum, max secure addresses. And you can see the range is 1 through 6,144. And if you're laughing, it's okay. The first time I saw that many max addresses on one port, I kind of laughed too. And the default is 1. Obviously, you can't set it to 0, because if you did, you'd be disabling it. And the key here again, the default is 1. I would not recommend putting 6,144 maximum addresses on a port, but that's the only reason. That's the reason we have the maximum command. Simply, what is the maximum number of secure MAC addresses we can have on this particular port. Now with MAC age, let's look at violation right now. Violation, this is the action that's going to be taken if there is a security violation. The default is shut down. I believe we saw that in show port security interface. I saw it right here next to violation mode. Zing, there it is. That's shut down. Our other two choices are protect and restrict. And we've been around Cisco certification exams long enough to know that if we have some options like that, we better really know the difference. We're definitely coming back to those, but I want to show you these right now. The default port security, again, it's shut down. And it does exactly what it says it's going to do. The port is placed into error disabled state. Very important that you know that. It's error disabled. Manual intervention is needed by default to reopen that port. So what happens there is you and I, as the network admins, have to fix the problem first and then do a shut no shut on the port. And with shutdown mode, an SNMP trap message is also generated. Now, I know you may think it sounds silly when I say we have to fix the problem first and then do a shut no shut on the port. Well, if you do the shut no shut first, it's going to be fine until the error happens again, which will probably just take a few seconds. Protect mode, it just drops the offending frames and no other action is taken. Our middle ground security mode is restrict, and the non-secure frames are dropped. There's an SNMP trap notification and a syslog message generated, but the port remains open. So if you want that port to remain open, but you want these other notifications, you need to go with restrict. But definitely I would know what all three of those modes do. So let's see, we've taken a look at violation and maximum. Let's take a look at MAC address here. Okay, so we've got Triple H, I like it, 48-bit MAC address. So we can put a MAC address in there if we want, apparently. And then we have something called sticky. Ew. For some reason, I always just see, Pepsi being poured into a router or something when they say sticky address. I have no idea why. Anyway, sticky addresses, configure dynamic secure addresses as sticky. We will do a lab on those, but that just means that these are addresses that are dynamically learned, but they are going to be kept on a reload. We'll do a lab with that as well. Let's go ahead and look at our other option here, our aging option. We have static, time, and type. Now, a configured secure address, a statically configured one, as you would expect, is not going to age out, because I can't think of anything that we configure at the command line statically that would age out dynamically or automatically. It's rare that you're going to want to do that. You may have very specialized situations where you want to enable aging for a configured secure address, but it's not something we do terribly often. Then we have time and type, and we've got the aging time in minutes, and you put anything in from 1 through 1440, so that's how long it would be before a dynamically learned address was actually aged out. And then you have your type, which is absolute and inactivity. The default is absolute, and that just means the clock starts ticking as soon as that address is learned. It doesn't matter how often it's refreshed. Inactivity, of course, the aging is based on the inactivity time period. If we don't hear from that source MAC address for a while, then we're going to flush it out. So this video, what we've done here is just an introductory look at the commands. We're going to go back to every single one of them during a lab and work with them, but I want you to see them all in advance. And what we will do here on the very next video, we're going to have router 1 or host 1 at 172.16.23.111, and then our other host is going to be at 172.16.23.222. We're just going to use that to send some pings and have some different source MAC addresses, that kind of thing. And like I said, we'll see all of these things in action. And we will start with that at the beginning of the very next video. I'll see you there. I did want to clarify on the diagram that Fast Ethernet 0/1 is the interface leading to host 1 and Fast Ethernet 0/2 is the one leading to host 2. We're going to see port security in action, and I'm going to use a secure MAC address different than the one you see on the board, because what we're going to do here is on that port leading to host 1, we're going to enable port security, and we're going to put a secure MAC address on there that cannot possibly match traffic that's actually going to come in from host 1. So what I like to do, especially in lab environments, not a bad idea for production either, is before, let me check that port. Before I start working with port security, I like to shut the port down. And I've already done that on 0/1. It's administratively down, because I don't want any traffic from something that I don't know is running or forgot was running to trickle in and trigger port security when I'm in the middle of it. Because right now, if I look at that table, our address table, you can see that it's empty. So right now I've got port 1 shut, so it can't possibly learn anything. And let's go ahead to fast 01, and we'll do a switch port security. That's to enable it. Then we can use our up arrow. And let's look at our options again. We've got aging, MAC address, maximum, and violation. Right now we're going to work with MAC address. And we've got Triple H, and we've got sticky addresses. So right now we're going to work with the regular MAC address type. We've got a lab with sticky addresses coming up later. And I'm going to define the all A's MAC address as a secure address. So far so good, and really that's all there is to it outside, of course, testing it. But let's look around at show port security commands before we do that. And you can see here's our secure port 0/1, one maximum secure address. The current count is 1 because it's counting the static one we put in. There haven't been any security violations yet, and a security action is at our default of shutdown. So let's look at address. And there's the VLAN 100, which by the way I've put both hosts into during the break. And there's the secure MAC address we've configured. And notice it even says type secure configured. That means that we statically entered it. Here are the ports that we're considering that address to be secure on, and our aging is disabled right now, so that's why we have a dash there. It's disabled by default. So let's run show port security. Let's use our up arrow there. And we're going to take it to the interface level. Very important difference I want to show you here. We see that port security is enabled, which is a good thing because we just enabled it. Port status secure down. I want you to take note of what this says when the port is administratively down, which it is right now, as opposed to what it's going to say if and when port security shuts it down. Everything else pretty much exactly what we'd expect. And here's the last source address it saw. That was during, and that's actually the source MAC address of the interface on host 1. So it's holding that because I did something with that during the break and some frames came in on it. But we have a security violation count of 0. So let's see what happens though when we do a no shut on that. And I'll save that. I'll go on over to 1 and send some pings now that the interface is up. And it may have already gotten some traffic, but we'll see how that goes. And let's see what we get here on switch 1. We send some pings from host 1. And we're getting something. And we're getting some more. And you know what? None of that looks good. Not one little bit of it. But it is what we expected to see. Because when those frames came in with a non-secure MAC address, first, the P-secure violation error detected on fast Ethernet 0/1, and the switch put fast 0/1 in error disabled state. Right with that, I don't even want to say after that because you see the timestamp. It happened at the same time. Here's your port security P-secure violation message. Security violation occurred, and it was caused, I know most of that one word is off, but it was caused by MAC address, and there's the address that caused it on the port. So we're even finding out what the non-secure MAC address is just from the console messages. Then we see the usual suspects as far as the line protocol and the interface going physically down. So let's start doing our show commands, because let's just say you walked in on the middle of this, or the exam or job interview or anything just plops you right in the middle of it, didn't show you these console messages like, okay, tell me what's going on. Well, first off, we could just look at the interface. We don't have to use a port security command to get some important information here. Now, we get a ton of info, but what we're really interested in is at the top here, the interface is physically down, logically down, and it's error disabled. That is the big important part right there. So now let's revisit our show port security commands. We'll start with show port security. And now the important difference from what we saw earlier, of course, security violation count is 1. So show port security tells you there has been a security violation on there. It's not giving you much more information about it though. So let's do show port security address. And this really looks the same as it did before because this is just showing you your secure MAC address table. It's not going to show you violations, anything like that. Where we might get some more good information is here. And show port security interface fast 0/1. Port security is still enabled, and note the status. It is secure and shut down. Just because you see the word down next to port status, it doesn't mean that port security has shut the port down. It just meant that it was down. And we know why, because it was administratively down. Everything else, here's your security violation count. That's the big difference right there. And again, it's even showing you the last source address, VLAN 100. And there you go. So we know now what it looks like with 4 different show commands and the console messages when a port goes down due to the shutdown mode in port security. So now you and I as the network admins have to do 2 things. First off, we have to fix the problem. We should do that first. And then we can reset the port. Because by default, if a port is error disabled, we have to fix the issue and then reset the port. It's not going to reset itself by default. So let's go ahead and take care of business here. First off, how would we resolve the issue? What do? We just take that static entry out. And there's no switch port. All I did was do a Control-A to move the cursor to the front and type the word no. Saves you a lot of typing. We can do a show port security address just to verify it's come out. And you can see now the table is empty. So now, this is interesting because what's going to happen when we reset the port? The port is going to have a maximum of 1 secure MAC address, but we have it statically configured in it. So that means that the very next source MAC address that comes in on a frame onto this port, that is going to be learned as the secure MAC address. That's the way it works. So let's go ahead and just do our shut no shut here. And we'll wait until everything comes administratively up as opposed to administratively down. And of course, we're going to check that interface before we go any further. And we can see now that we have gotten rid of the error disabled message. So that is a good thing. Now, let's see. I don't think that we've learned that address yet. So let's go over to 1. And we'll send those pings again. And we're sending some pings through that switch, so let's give it a few seconds here. We haven't seen any secure violations, port violations, anything like that so far. Is our interface still up? Should be. Yep, it's still up and up. And there is our dynamically learned MAC address, secure MAC address. You see the big difference here is that the type is secure dynamic. So for a source MAC address to be considered dynamically secure, there's got to be a difference between the number of maximum addresses the port can learn and the number that it's actually learned. So we see now that since we had the port set for 1 address to be learned and no static configurations, the very next address it learned, very next source MAC address, was going to be considered the secure one. So we're good there. Let's go ahead and just run show port security. And we can see that it has indeed learned 1 address. We just verified that by looking at the table. And more importantly, much more importantly, the security violation count is empty. So finally, you think I'd remember that after all these years. Interface fast 0/1. And we can see the combination we really like to see, that port security has indeed been enabled. We knew that part, but finally the port status is secure and up, and that is what we want. You can also see the security violation count is now at 0. The last source address, VLAN, is the same as it's been. So that is port security in action. That's our shutdown mode. And in the very next video, I think we're going to go over to switch to host 2 and work with that port a little bit, and you'll see some other real world scenarios in action. I'll see you on the very next vid. Just taking a look here at our secure MAC address table, and we're going to make this grow a little bit. We're going to work with fast Ethernet 0/2, the port leading to host 2, And we're going to configure some secure MAC addresses that we know aren't going to work, and we'll play with the maximum a little bit and see what happens. It's going to illustrate a point that I was describing in the last video as well. So let's go ahead and go to interface 0/2. First thing I'm going to do is shut it down because I don't want it learning anything while I'm in the middle of this config. So let's go ahead and enable port security to begin with. And now let's change the maximum here a little bit, see what that looks like. Like I said, I wouldn't go to 6,144 secure MAC addresses on a port. Let's set it for 3. And now I'm going to use the MAC address option again. And we'll go with the static one. And I'm going to try to make up another one on the fly here. Hey, it worked. So we've got 2 addresses defined, but we're allowing the port to have 3 secure MAC addresses. So the theory holds that the very next the very next MAC address it learns on that port will become a secure dynamically learned address. So we're going to test that theory out, and let's go ahead and look at our tables here again before we get started. Show port security. You can see the 2 configured addresses are already in there, and you can see they're labeled as secure configured, and you see the port numbers as well. And let's do a show port security interface fast02 while we're here. And again, it's secure and down for port status because the port is administratively down. 3 MAC addresses, 2 total, 2 configured, no sticky. It hasn't seen anything come in on the port, so you see a last source address of all zeros. And that's it. So let's go ahead and do a no shut there. I know that address had to come, the interface had to come up. 23, one will ping host 1. And I sent the pings and then came back on over to the switch because I didn't need to hang around to see them go through. And we don't see any port security messages, so that's always a good thing. So let's go ahead and look at our address table. And you see now 2 secure dynamic addresses. And one of them, the new one, is for Fast Ethernet 0/2. These are all secure MAC addresses for 0/2. We sent a max of 3, 2 configured, 2 static ones. Of course, that let it learn the next MAC address it learned as a dynamic one as well. So we've got 1 secure dynamic and 2 secure configured, all for Fast Ethernet 0/2. Nothing to it. And let's go ahead and run. I should be able to up arrow to that one. There we go. And that's it. And we see now that great combination, port security enabled, port status secure is up. Maximum MAC address is 3. Now the total overall is 3. 2 of them were configured. 1 of them is dynamic. That's the one column they don't have here. They do have a column for sticky addresses, which we will be working with soon. And there's the last source address that it saw come in on that port and the VLAN. So that's it. That proves the theory. And we always like seeing that stuff work. So you want to watch that if you got a difference between the total number of addresses it can learn and the number of static addresses. Because you may want this. You know, this may be fine for your purposes, but then again, it may not be. So just be aware that that's what can happen. That's the end of this lab, and we'll work with another port security feature on the very next video. This is going to be an important video for more than one reason, and one of the reasons you're seeing on the screen right now is that we're looking at the aging command. And I was just doing this as I was uploading the last vid. And just going through the choices, and I want to review these with you one more time as far as aging goes. Now the aging of static entries, statically configured secure addresses, again, not something you're going to do terribly often, but it's good to have the option. With type, you're looking at absolute, where the clock starts running, and that's just it. Inactivity is aging based on an inactivity time period when we say, okay, if we don't hear from you for so many seconds or so many minutes, then we're going to drop you out. And again, absolute is the default there. Now, a quick CCNA review. Do you remember what the time, how long a dynamically learned MAC address stays in the table if it's not heard from again? 300 seconds, right? And we have you learn it that way because 300 is the way you have to put it in if you want it in for 5 minutes. So just playing around here, we're going to go ahead and set this for the same value. And nothing to it, right? So you just put the aging time and then the value in that you want. And I wanted 300 seconds, so that's what I put in. And how would I verify this? MAC address. Yeah, because here's one way to do it. You've got remaining age 300 next to the dynamic address that was learned on 0/2. So there you go. So I got it right, right? And if this is the first time you're watching the video, I hope you're saying, no, you're getting it wrong. This is the other important reason that I'm showing you this command. And it's a little bit of a dad lecture, as I tend to call it, but I don't want to laugh it off because this is really important stuff. And those of you who got your CCNA with me, I'm pretty sure you know what I'm about to say. Anytime that you are using a command in the Cisco iOS that has any unit of measure, whether it's time, data, anything else I'm not thinking of right now, always use iOS help to see what the unit is, especially with time, because sometimes your commands will take seconds, sometimes they'll take minutes, sometimes they'll take seconds, hours, days. I mean, there are a lot of different ways to combine these things. And if you think, you know, okay, I'm going to set this to 10 minutes, and you enter 10 in for the value, but it's being entered in seconds, then obviously you're not going to get the answer that you want. You're going to have a bad time. And you're going to miss an exam question too. We don't want that. The problem here, and let me just go right back to 02. The problem here is that with aging time, it's aging time in minutes. So if I wanted to set this to 300 seconds, I would not put 300 here, right? I would put 5 here. That's what I would need to do. And the reason I bring that up is because the command to change that for the MAC address table is MAC address table aging time. I've got an extra dash in there. MAC address aging time, and you set this in seconds. This is the little kind of thing that causes you big problems on the job. And of course, it can cost you points on the exam. And again, we don't want that. I'm not saying you got to memorize every single value of every single command in the iOS. That would be silly. Knowing these two, I think, is a good idea. Again, if you are changing the aging time for your secure MAC address table, that is the switch port security aging time command. And that value is entered in minutes. If you're changing the aging time for your general MAC address table, then you're doing that in seconds. And that's a really good habit to get into, period, on the job and on the exam when the simulator engine lets you do it. Again, always check your iOS values like that because, like I said, some are in seconds. There's no way to memorize all of them, and you don't want to do it anyway. So that is it for this particular video. So a good reminder there about your iOS check, and also about changing the aging time on your secure MAC address table as well as your general MAC address table. We are going to take a look at those dreaded, nasty, sticky addresses in the very next video, and we'll see them in action. I'll see you there. I wanted to show you a couple things about our address table at this point, our secure MAC address table, that is. And first off, the rather restrictive aging that we enabled at the end of the last video has taken effect because the dynamic entry that was on 0/2 has now totally aged out. The one we have on 01 is still there because aging, as with just about everything else we do with port security, it's on a per port basis. So we didn't change aging on 0/1. Now, the only issue with a dynamically learned secure address is that on a reload, we're going to lose it. That entry will be flushed out. That'll actually happen if the port just gets reset. If I do a shut, no shut right now, I believe we will lose that address. Let's go ahead and give it a try. We'll do a shut, and then a no shut for it. And you can see it's actually been removed, and I'll do that one more time. Now, of course, with one address, you could say, well, is it really that big a deal for the switch to have to relearn one dynamically learned address? I would say no, not really. But of course, we could have dozens of dynamically learned addresses, and maybe we want the switch just to come up and already have those if it's reloaded. Let's see if it's learned that again yet. Yep, there it is. So it didn't take long. We had some other traffic come in, and it was carrying that MAC address, and it's been listed as secure dynamic. But what if we want that to be kept even if the port goes down? What if we want it to be kept even if the switch is reloaded? That's where sticky addressing comes in. What you're doing with sticky addressing is these secure dynamic addresses are then written to the running config. So they're kept on a reload. You just do a yes when it says you want to save your work if you haven't done it yet. When you reload the switch, and it's going to save them. And when the switch comes back up, the addresses are already there. They don't have to be learned again. That's not a bad deal. So let's go ahead and enable that on that particular interface. And it's switch port security. What now? There's no sticky option. Where is it? It's in MAC address, and then sticky is at the end of that. And there are no options. We're always happy to have no options there. So now let's run show port security address and notice the change under type of that same address. We've seen it as secure dynamic for the last couple of videos because frankly that's what it was. But now it's listed as secure sticky. So let's go ahead and shut that port down. And usually that'll get rid of your dynamic addresses in a heartbeat. And it would here too, but this is no longer a dynamically learned address. It is a sticky address, and therefore it's going to be kept in that particular scenario. So I will go ahead and do a no shut. And it's going to say the exact same thing. But again, it's going to be kept on a port reset or even a switch reset. It's a pretty cool feature. Actually, what we will do, I am going to pause this video because this switch does take a few minutes to reload, but I'm going to go ahead and just reload the switch. And yeah, I want to save my changes. System config has been modified. It's going to ask you if you really want to proceed with the reload, and I said yes. So what I'll do is go ahead and just pause the video right now, and once the switch comes back up, I will unpause the video. I'll do a shut no shut on the video, and we'll see if those addresses are still there after that reload. And we're back. Just wanted to show you some of the stuff that we're going through here, and I did indeed reload. And you remember what POST stands for, right? What are those? Power on self-test, little test it runs before it really starts booting. So all our posts passed and everything. We got the warning about the cryptographic features, don't mess around, and some information there about the switch itself. And then finally, once we got through the intro messages, I ran show port security address, and there is the address. It's still listed as secure sticky. So some good stuff there. That's all a sticky address is. That's all there is to it. And on the very next video, we're going to go back to something about the error disabled ports. Because I'm sure you remember I put a little emphasis on by default, error disabled ports have to be manually reset. There is a way around that. It's not really a workaround because it is a Cisco feature. It's built into the switch about automatic recovery from an error disabled status. And I will show you all about that, and we'll test it on the next vid. See you there. We're going to see the error disable recovery mode in action, I hope, here in this particular video, in this particular lab. And the change that I've made here on Fast Ethernet 0/2, the only one really, you can see it's secured down next to port status, so you know that I have the port administratively shut down. But what I've done is changed the maximum MAC addresses to 2. We had it at 3, and we know that we have 2 statically configured ones for that interface. We've seen that in several of the past videos. And as a matter of fact, I'll just review it right here. We know we still have those 2 configured addresses from an earlier video. And since we set maximum MAC addresses to 2, now it can't learn 1. So when that source address of 001B D4C2090 comes in, the port should go into error disabled mode, and we know what we have to do from there. But before we open that port and allow that to happen, we are going to put error disabled recovery into action. And we're going to do that with the error disable recovery command. And by the way, I know that there always seems to be a hyphen in error disabled, but in this command there actually isn't one. So we've got error disable recovery. Let's try that again. And we've got cause and interval. Notice that this is not a port level command. I think this is the first non-port level command we've really run into with port security. That's because this is not a pure port security command. As you're going to see in a moment, you can use it for just about anything that's going to that can put a port into error disable mode. So we've got error disable recovery. Let's go with cause first. And this is a lot of causes. That's a lot of causes, a lot of different ways that a port can go into error disable mode. They barely actually don't quite fit all on one screen. So you do have the all option at the top where it enables the timer to recover from all error causes. That's a little heavy for us right now. We're going to stick with the port security. Pardon me, goodness, the port security violation. And that is right here with P-secure violation. So that's what we're going to go with here. And we're always happy to have no options. So really that's it. First you have to pick the cause. And let me show you, there is a show error disable recovery command. And this is going to show you whether it's been enabled or disabled for every single one of those reasons. And you can see the only one it's enabled for right now is our port security violation. The other important value we see at the bottom is the timer interval 300 seconds by default. We're not going to stick with that. It's also going to list the interfaces that will be enabled at the next timeout. And in this case, there aren't any because we don't have any that have actually been put into error disabled mode because of a port security violation. Let's call this command back up. And we're going to change that timer. Okay, interval. Got me. Interval, and the minimum we can set it to is 30 seconds. So there's no such thing as an instantaneous recovery attempt from error disable mode. So let's go with 30. And no options, and so far so good. We'll go ahead and verify that before we open that port and make the port go into error disabled mode. And let's try that again because I came out of it too early. There we go. The timer interval's been set to 30 seconds. So we're all good there. Let's go ahead and open that port. And I will stand by to send some pings when I see the interface come up. And let's give it a moment here and see if we end up in error disabled mode. And there we go. So we're seeing what we expect to see. We're seeing that because of a port security violation was detected and it's been put into error disabled mode. I'll go ahead and run the interface command. Actually, let's run show error discovery. And now you can see at the bottom that port is listed interfaces that will be enabled at the next time out, and time left is 11 seconds. Grab a swallow there, and now we're getting a message that we haven't seen before, and we'll see if this is successful. It looks good so far. And you can see it's an error recovery message attempting to recover from P-secure violation error disable state on fast Ethernet 0/2. Then the interface comes up, and then the line protocol comes up. And now we're getting another port security message. And this is why I was hammering early. You know, we always have to fix the problem before we try to bring the port out of error disabled mode. And that's the problem right now, of course, is going to keep going into it as long as it keeps getting some kind of data from host 2. So it is not perfect. It's not going to fix the problem for us. But what we need to do here is just go ahead and make the maximum of 3 addresses, something like that. And then when it comes out of error disabled state, it will stay there. But I did want to show you that particular feature. So let's go ahead and try to get that fixed. We're going to do an interface fast 02 first and do a shut. So we don't have to keep running into that. And then we're going to do port security. Nice try. Max 3. And let's see if that works. Let's see what happens here. Let's just sit back for the ride. I'll take a sip while you take one. So everything's come up so far. Let's check our address table. Actually, our error recovery table. Looks like everything's good. And we're enabled, secure up. We love that. And you can see the maximum MAC addresses did take effect. And now we are showing 3 total MAC addresses. And even better, no security violation. And that's it. So now we have 1 secure sticky address, 1 secure dynamic address, and 2 secure configured addresses in our table. And you also got to see the error disable recovery mode command, which in the right place is a fantastic command. That wraps up our time with port security for now. We're going to head into .1x based security next. And then after that, we'll do some span and some other great stuff. So I'll see you in the very next video. As we begin our study of BGP, I'm starting with a quote from one of my favorite books, one of my favorite movies, one of my favorite TV shows ever. I will spare you my Charles Kingsfield impersonation, but when he says, "The study of law is something new and unfamiliar to most of you, unlike any other schooling that you've ever known before, the same can really be said for BGP." And here's the entire deal with BGP. It is unlike anything you've studied to this point. So if you haven't seen this before, don't expect to absorb it all the first time you see it in action. The rules are different, the concepts are different, the terminology is different. Just about everything is different from the IGPs that you've studied to this point, like OSPF and EIGRP. Now, it throws a lot of people for a loop the first time they see it, and that included me. And the key to initial BGP success, and really all BGP success, is to take one concept at a time, and then one attribute at a time, and before you know it, you've mastered the fundamentals of BGP. And what I'm going to do in this part of the course, which is the largest part of the course, is when we get to the attributes, which will be soon, I'm not going to just hit you with 12 of them and then we're going to go back in the video and look at them. You're going to see every single one of these attributes in action. You'll see exactly what they do. So there's some good stuff here. It's just new stuff for many of you. And for those of you with one eye on the CCIE down the road, this is some of the most important study you'll do. Because, of course, it's true of anything. If you don't have the fundamentals down, you can't really master the advanced skills. But with BGP, as you'll see, it is particularly true. Now, the first natural question is, well, if BGP is so different, if it's not really like EIGRP or OSPF, what the heck is it? Well, here's one definition for you: an internet protocol that allows groups of routers called autonomous systems to share routing information so that efficient loop-free routes can be established. BGP is commonly used within and between our internet service providers, the ISPs. Now, that definition started sounding a little bit like EIGRP, right? I mean, as soon as you hear autonomous systems, you think EIGRP. Well, both EIGRP and BGP use autonomous systems. We're actually going to be typing in some AS numbers here in our BGP labs as well as we did in our EIGRP labs. Both protocols use that term to refer to a logical group of routers. And the difference comes in really where BGP fits in the big scheme of things, because BGP is an exterior gateway protocol that runs between ISPs, where EIGRP is an interior gateway protocol that runs in the networks connected by the ISPs. I've always put it this way: BGP runs on top of OSPF and EIGRP. It runs higher in the big scheme of things. Now, BGP also shares some other characteristics with EIGRP. BGP supports VLSM and summarization, and we'll do some summarization here in one of the labs. BGP sends full updates when routers initially become neighbors, or in BGP speak, really peers, and after that, BGP will only send partial updates reflecting the latest network changes, because BGP updates can literally contain tens of thousands of entries. And in that case, we really don't want those going out, say, like RIP does every 30 seconds and then send the full table. That would not be efficient. Now, BGP, as I mentioned, we have peers, we have neighbor relationships, the same thing. They create these relationships before they exchange routes, and there are keep alives that are sent to keep the adjacencies alive. And of course, we know the deal here. If those keep alives disappear, the adjacency is gone. Now, BGP neighbors exchange much more information, much more extensive information, I should say, about networks than our IGPs do. Now, the additional BGP path information comes in the form of those attributes that I mentioned a few moments ago, and these path attributes are contained in the updates sent by BGP routers. And we're going to master these attributes, especially the fundamental ones, because they are the key to success with BGP. And it also starts with knowing which ones are what we call well-known and which ones are optional. And if these are terms you've heard before, we're going to go over those lists. Believe me, if you haven't heard them, don't worry about it because we're going to get to it in the next video or two here. We got a little folderol to go through before we get to the labs, though. A few rules we need to know. And right now we're going to take a quick look at some general Cisco best practices regarding when BGP should and should not be used. Now, when BGP should be used is when your company is connecting to more than one AS or ISP, because decisions on the best links to use can be made by utilizing these BGP path attributes. We will see that live. The routing policy of your organization and your ISP just may differ a little bit. That's when BGP can come in handy. And if your company is an ISP to begin with, because when traffic from other autonomous systems use your AS as a transit domain, BGP will definitely come in handy. So in short, if your AS has more than one connection to other ASs, or other ASs are using your AS as a transit domain, you'll definitely be using BGP. There are a few circumstances when you should not use BGP. When there's a single connection to the internet or to another AS and no redundant link exists. When you don't care which path is used to reach a route in another AS, you may have that situation. And when router resources are limited, again, as always, that's a relative term, but BGP does hammer the memory and the CPU quite a bit. And also, when there's a low bandwidth connection between multiple ASs, in that situation, we may go with some static and default routing instead of running BGP. Now, all of this will become a little more clear, first off, when you watch the video more than once, but secondly, when you see BGP in action. And at the beginning of the very next video, coming up next, we're going to get our first BGP adjacency built. We're going to take just a minute or two here to go over some theory of BGP peering before we actually start performing it. And this is very important stuff. You're going to see it's very simple stuff, but it's very important because, of course, without the peerings, we really don't have anything else going on. But also, we have to watch what kind of peerings we have because that's going to impact the operation overall of our BGP deployment. TCP, just like TCP, BGP is connection-oriented. It's considered reliable. And we're going to have an underlying connection between two BGP speakers before the routing updates are actually exchanged. Now that connection takes place on TCP port 179, which is a port you've got to leave unblocked by access lists or anything else you happen to be blocking stuff with on your Cisco routers. Once that connection is established, the BGP speakers exchange routes, they're going to sync their tables, and then after that, the initial exchange, that is, a BGP speaker sends further updates only when there is an actual change in the network. Now, BGP speakers do not have to be in the same autonomous system in order to become neighbors and or exchange routes, as we're going to see in just a moment. We have two different kinds of peerings, and this is what you got to watch. Our adjacencies, we can have an internal peering or an external. Now, a BGP peer in the same AS as the local router is an internal BGP peer, just like we see here on the board. Both routers are an AS100. That's an IBGP adjacency. And a BGP peer in another AS is an external peer. Makes perfect sense, nothing difficult there at all. But you got to watch that little I and that little e, because that's the way it's going to show up sometimes in your BGP tables and also in the diagrams that we're going to be seeing throughout this section. Cisco recommends that eBGP peers be directly connected. IBGP peers are not required to be so connected and generally will not be. Now we're going to start our very first adjacency here in our first lab with the router BGP command, followed by a neighbor command to identify this BGP speaker's potential neighbors. So let's go ahead and bring the live equipment up. And we're on router 1. Routers 1, 2, and 3, by the way, are over the same frame relay network that we've used over most of the labs in this course. But I'm not showing it here because it's really not germane to what we're doing. We're looking above that. We're looking strictly at BGP. So router 1, let's start there. And with router BGP, we have one option and one option only, and that's the autonomous system number. For our lab here, we're going to put router 1 in AS100 and router 3 in AS300. Actually, that's actually an example. Let me go right down here. This is the adjacency we're going to build. And it's an eBGP adjacency between router 1 in AS100 and router 3 in AS300. So we start here with 100. And looks pretty familiar so far, right? You know, looks familiar. And we're going to do our neighbor command here. And we've got an address or an IP version 6 address or a tag. We're going to stick with our traditional version 4 address for right now. 23.3. And holy cow, that's a lot of options. And you'll notice we're only through the P's. Do not panic. You do not have to know every single one of these for the route exam. I'm not even sure you have to know every single one for the IE lab. There's some stuff in here that I haven't used, and I've been using BGP for an awfully long time. And let's look at a couple more options here, but notice the one thing you don't see at the bottom is a CR. So you've got to put something here. You don't just put a neighbor command. And one of the requirements, the requirement really for a BGP deployment, you got to specify the neighbor. There's no dynamic discovery here. You've got to specify the AS of this neighbor that you're entering. So we're going to put remote AS, and again, you've got to put the AS of the remote neighbor, which is going to be 300. Now we know that this adjacency is not complete because we haven't gone to the neighbor and done anything as far as BGP config. But what I want to show you right now is your first verification command, which is show IP BGP neighbor. And you can also follow that with the IP address of the neighbor if you just want to see this information about one. And that can come in handy when you have a lot of BGP neighbors. But looking at top to bottom here, BGP neighbor is 172.12.123.3, makes sense. There's the AS number of the neighbor, and it's an external link. Okay, so far so good. BGP version 4 is what we're running. And there's no RID here indicated for the remote router because we know we don't have an adjacency. There's no way to have a RID. Notice the BGP state of active. Sometimes, as we've seen, active is good, and sometimes active is bad. And there are some other BGP states that you might not see here during these labs, so I want to show them all to you right now. And this is important stuff because it really helps you spot the issue. And first off, our states, we start with idle, and that's the initial state of a BGP peering. And if you have a connection that goes to idle and stays there, I can practically guarantee you it's going to be one of these two things. 99.9% of the time, it's going to be one of these two things. Make sure that the IP address in the neighbor statement is the one you meant to use. I know that sounds silly, but everybody mistypes a number sooner or later. I do it, you do it, everybody does it. Make sure the IP address in the neighbor statement is correct, because you're going to spend 20 minutes one day troubleshooting the complicated stuff, and then you're going to come back to that and say, oh, I can't believe it was the neighbor statement. Check that first. Be sure the local router knows how to get to that particular IP address, because I have a feeling in some of our more advanced labs in this section, reachability may be an issue. Here it's not an issue because they're all on the 172.12.123.0/24 network. Now, connect follows idle. Now, in connect state, a TCP connection request has been sent, but a response has not yet been received. Now, if the TCP connection completes, BGP will move to what we call open sent. If the connection does not complete, the state goes to active, and that's where we are right now. You'll only see connect if you happen to run show IP BGP neighbor at the right time. It's not going to stay in connect state. It might go to idle and stay there for the reasons we talked about, and it might go to active and stay there because we're seeing that right now. Active means the BGP speaker is continuing to attempt to create a peering with that intended neighbor. And basically, this is the halfway point of the connection. The local router has successfully sent a BGP open packet to the potential neighbor, but it hasn't heard anything back. And that makes sense because we're on router 1, we've configured BGP, we've got a remote AS statement, everything's good there, but we haven't gone to router 3 to finish. So it makes sense that this is the state that we're in. As with idle, there's nothing wrong with seeing active for a few seconds, but when you see your connections stay there, then you've got a problem. In this case, first off, make sure that you have BGP configured on that neighbor. Check the remote router's neighbor statement, make sure the AS numbers are correct. You've been taught so often with EIGRP, the AS has to be the same, the AS has to be the same, the AS has to be the same. And sometimes when you're starting with BGP, you'll enter the same AS as you just put on that remote router, even if it's not the one you're supposed to put on there. It's a hard habit to break. Now, open sent, that indicates the BGP speaker has received an open message from the peer, and what BGP is doing at that point is determining whether the peer is in the same AS or a different AS. Open confirm has the BGP speaker waiting for a keep alive. If one is received, the state moves to established, and that is the end game. That's what we want, the established state, because it's in that state that update packets are finally exchanged. So with all that said, let's go back to the live equipment, and I want to show you something here at the very bottom of this output. And some helpful information here. Connections established 0, so we've never had one. How many have been dropped? When the last reset of this connection was. And we're being told no active TCP connection. When we see this, we know there's an underlying issue, period, and there's no use to get complicated with your solution. We're going to fix this in just a moment by going to router 3 and finishing the config. When you have resolved the no active TCP connection issue, you're going to see a ton of extra information here. This is a verbose command when everything is up and running. So, speaking of that, let's go over router 3 and make everything up and running. Router BGP, we know this is an AS300, and our neighbor, 172.12.123.1, remote AS100. And let's see if something good happens. Something good happened right there. There's our BGP message. Adjacency change, neighbor 172.12.123.1, up. And up is always a good thing. So let's run show IP BGP neighbor. And again, just a quick reminder, if you want to filter this output, put the one IP address in there. And you're gold. Now, let's see, going from top to bottom, with show IP BGP neighbor, there's your neighbor ID, IP address, remote AS. This is an external link. Notice now we see a RID for the remote router. That's always a good thing. And here's what we really want. BGP state equals established. And right now it's been up for 21 seconds. And we go to the bottom and you'll see some information here. Here's IPv4 unicast. And notice now where we see connections established 1, dropped 0, last reset never. You don't see, just TCP is enabled, the connection is enabled. You're going to see a lot of extra information. Local host and foreign host. Foreign host, that sounds kind of aggressive. We're supposed to be peers and neighbors, and here we are with this foreign host stuff. Well, the important part is there's your local port 179 information. That's the port that was used to get the whole thing started, and you've got to leave that unblocked by everything. So right now we are up and running, and I'll go over to router 1, show IP BGP neighbor 172.12.123.3, and we see the exact same information. And again, there's the important part right there. BGP state equals established, and this is what we got to keep our eye on, that external link. So we're looking good. We've verified our first adjacency. After building our first adjacency, everything looks good there. And this is where we're headed next. We're going to bring router 2 into the mix, but we're going to put router 2 in the same AS as router 1 and then build from there. See you on the next vid. Time to move on to our first internal BGP peering. We're going to build that between routers 1 and 2. Router 2 down there at 172.12.123.2. And first off, though, I hate to start a video with a mistake. I'm making this one on purpose, so it doesn't count. Router BGP 100. What happens, let's say, if you're just typing right away and you try to make yourself the neighbor? Think that's going to work? What do you think is going to happen with that command? It's not going to work because you can't make yourself the BGP neighbor. You would be peering to yourself, and there's just something terribly wrong with that. Not to mention illegal here. You're going to get a message that says can't configure the local system as the neighbor. So if you get that, it freaks you out the first time, like any error message. First time it's like, huh? And it just means that you put your own local IP address in, or one of your local IP addresses in. Now let's try 123.2 there instead. There we go. I knew I had it in me. And then on router 2, we haven't done any BGP config at all. So let me move that back up. We'll start with router BGP 100 and neighbor 172.12.123.1 and our required statement about the remote AS. And we'll give that a few seconds to cook and see what happens. Usually just as I leave it, it ends up coming up. There we go. So it didn't take long at all. There's our adjacency change. Your neighbor is up, 172.12.123.1. Now, we know one command to see our neighbor information, and let's try it on router 2. Show IP BGP neighbor. We know that we can filter this by specifying the IP address of the neighbor, but we also know right now router 2 only has one neighbor, so there's no reason to do that. We know to look for the BGP state of established. We see that. We love that. This also shows you how long the adjacency or the peering has actually been up, what the remote RID is, etc. But wouldn't it be nice if we had a command that gave you just really what you needed to get started or double check your config without going, say, through, I don't know, the 5 screens of information that I'm showing you right now, most of which you really don't need at this point. And there is such a command. You'll be using this one much more often than you use the neighbor command, but it's a good idea to know both. And that is show IP BGP summary. And this is a great command. Now I've got a little hanging off because I make the font as large as I can to make it easy for everyone to see. The only thing hanging off there is a state of 0. And what we're really interested in, frankly, is the neighborhood and the AS and the up-down values. A couple of these we're just not concerned with right now, but you can see 172.12.123.1, and actually then you go over its AS100. We see it's V4 for version 4 of BGP. And it's going to show you how long it's been up or down, and we're up to 1.5 minutes. You also see message received there, incremented, message sent hadn't yet, but those are our hellos. And if we go up to router 1, run the exact same command, that's going to give you the same kind of information. And you can see here state PFX received all on one line. I'm not sure why it's on 2 lines in the other one, but this works out for us. It shows you first off your local router BGP RID, which is 172.12.123.1, shows you the local AS number, and what we really like is from left to right, gives you your neighbors, the version of BGP you're running, the AS they're in. You can see message received and messages sent coming in and hopefully continuing to increment. And you'll also see that up-down value hopefully just keep ticking while it's up. That's all there is to an iBGP adjacency. And right now, we're going to start on using our loopbacks for BGP adjacencies. Now, so far we haven't done that, but here's why we usually do in production networks and why we'll actually change it to be using a couple of adjacencies in our lab. Now, there's nothing necessarily wrong with using physical interfaces to create BGP adjacencies. But in production networks and in labs, you're more likely to use IP addresses from loopbacks because physical interfaces can go down for a number of reasons, but the only way a logical interface really goes down is if someone intentionally deletes it or the entire router is unavailable. In that case, you have much bigger problems than lost adjacencies. Now, if you use loopbacks, you've got to include a couple of extra commands, and this is one of those things that catches you, but you don't want it to catch you on exam day. It's not going to, because you'll know first off, it's an odd little BGP role. Loopback interfaces aren't considered directly connected, even if they share a common subnet. You'll need the eBGP multi-hop command when configuring eBGP adjacencies with addresses that are not on the same subnet. So you'll need that anytime you're using loopbacks. And when these addresses are on loopback interfaces, as they will be in this lab, the next one, you'll also need the update source loopback command. And we'll see that, and what it's actually asking for is the interface that you're using for your update sources, and that would be loopback 0, whatever you happen to number it. Now, there's a couple of rules to remember for loopbacks, using loopbacks for BGP, but there's one more, and this is so fundamental that it's really easy to overlook. So we're not going to do that. If you use loopback addresses for eBGP adjacencies, particularly in a simpler lab like we're doing right now, you probably need to configure a static route on each one of your routers that points to the remote router's loopback. Because if your local router doesn't have an IP route and doesn't know how to get to the address specified by neighbor, I mean, you're stuck before you begin. We've got an eBGP adjacency in progress here on the board between a couple of routers. I've got neighbor 3333 remote AS 200 on the one on the left, and that router is basically saying that's fine, but how the heck do I get to 3333? What do I do? And we're going to see all of these concepts in action in our next lab, where we create an adjacency between 1 and 3 using their respective loopback interfaces. Now, I say here in the book that the previous BGP configurations have been removed. I want to do that here live. It's not hard to do, but I do want to remind you of a quick way to get that done. So we're going to go under router BGP 100, and what I want to do, I'm going to go up till I see my 3. I might not still have that one. Okay, I don't. That's fine. Let me go in here and just change that to 3. And what you can do with this kind of command is just do a Control-A, move the cursor to the front, and type no. I'm not huge on keyboard shortcuts. It's not something I do a lot of, but I really like Control-A, because if you just go through your history with page up and page down, you see a command you want to negate, then you just stop right there, do Control-A, the cursor moves to the front of the line, just type the word no, put in a space, and you're good. Now what I will do, and of course we're going to get an adjacency change saying, hey, you don't have that, that adjacency you just deleted? You don't have that anymore. Let's go up to router 3, router BGP 200, and I could have just taken BGP off of this. I could have done a no router BGP 200, but instead I'll call that command up, Control-A, moves the cursor to the front of the line, type no, hit the space bar, and you're gold. That's all there is to it. During the break between videos, what I'll do is create a loopback on routers 1 and 3, 1111 and 3333, as you would expect at this point in the course, and then we'll create an adjacency using those loopbacks instead of the physical interfaces we used in the previous video. See you there. Just to prove that there's absolutely nothing up my sleeve, you can see at the top of this screen that router 3 has the loopback 3333 created, 32-bit mask, a host mask that is, and just to verify there's interface loopback 0, and on router 1 we have a loopback 0 as well, IP address 1111 with a host mask. So let's proceed now and get that adjacency back up and running. We're going to take it one step at a time and put one command on router 1 and then the corresponding one on 3, so we can keep checking the adjacencies. And right now, let's go with the remote AS command. Nice try. So we're putting 333 in this time, and then remote AS 200. And we'll just give that a moment, and I'll run show IP BGP sum on this side. Just want to get you used to seeing the different stages. There's idle for a state, so nothing much happening here yet. Let's go over to 3. And let's see. Pardon me. BGP summary. And you can see, I'll have to move this one over just a little bit, but you can see the state of idle over there all the way on the right-hand side. So even though last time, we did the peering between 1 and 3, this is all we had to do. But we weren't using loopbacks, we were using the physical interfaces that were on the same subnet, so we were able to just go right ahead and use the neighbor command, and that was that. Now we need an eBGP multi-hop command. And just for the sake of foolish consistency, I will start on router 1, and let's have a look for that command. And there it is right in the middle. eBGP multi-hop allows eBGP neighbors not on directly connected networks, and we are working with eBGP here. So, gotta get that tricky little dash in. And just one, please. Multi-hop. And you do have a value of 1 through 255. It's a good habit to get into keeping these values as low as possible while still getting the job done. It's also a good habit for Cisco exams because they tend to ask you that kind of thing. And 2, right here, my friend, will do the job. So let's go over to router 3, put that same corresponding command in. And now we've got that set up. Let's run show IBGP sum. And we're still kind of sitting here. We're sitting here kind of idle. Let's see what router 1 says. Router 1 says it's active, so we got something going on in there. We went over all these states earlier, but we know, just like with EIGRP, we don't want this to stay active. We want it to go to established. That's what we're looking for. So now we're going to use our update source command, and we'll do a conf t router BGP 100. And this one's, as you would expect, since it begins with U, is all the way at the bottom, source of routing update. So we're going to say update source, and then you just put the physical interface. Notice that it's not asking anywhere here for an IP address, so we need to go ahead and put loopback 0, and that's where they're coming from. And in 3, we're going to put pretty much the same command. Update sour loopback 0. And so we've got our 3 commands here for neighbors when we're using loopbacks and we have an eBGP relationship going on, or appearing that we want to have going on. We've got the remote AS command, we got eBGP multi-hop, we got update source, and we still have an incredibly idle situation. Let's go over to router 1, and I think we're going to see active. Maybe, yep, still active. So everybody involved is trying, but of course we know what the issue is. We discussed it at the end of the last video, and this is where static routing comes in. Because router 1 doesn't have the faintest idea where the IP address 3333 is. Router 3 doesn't have any way of knowing where 1111 is, so we could work in a routing protocol here, dynamic IGP, but instead we're going to go ahead and use a static route. It's good practice too, because it might have been a while since you made a static route. What comes next? Pop quiz, what comes next? We're going to put the address in, and since we're going to make this a host route, which matches only one address, what am I putting next? Is it all 1s or all 0s? That one is going to be all 0s. It's a prefix mask. And then you could put either the next hop IP address, which I prefer to do, or the local exit interface. I'm going to put 172.12.123.3. Then I'm going to go over to 3 and put in a mirror, if you will, to 1111. 12.123.1. And boy, that didn't take long, and there you go. That's so easy to overlook. You'll never overlook it, exam or production or lab, once you see it, but it's so easy because you're just so consumed with the new commands. And you keep looking, it's like, okay, I got the right remote AS, I got the right neighbor, I got eBGP multi-hop, I got update source, etc., etc. But you just needed to remember that 1's got to know where that remote loopback is, and 3 needed to know where router 1's loopback was. So let's go ahead and check out our situation on router 1 just in case. And that is what we like to see. Now we've got our neighbor adjacencies back. Notice now that the neighbor is 3333, not 172.12.123.3, as we had before, and everything else looks exactly the same. So we are done there. Coming up next, we are going to advertise our first routes in BGP using the lab that we have built to this point. I'll see you on the next video. With a couple of peerings in place, let's get ready to do some advertising of routes with BGP. And of course, we'll have to create a route or two to advertise as well. Now, we are going to use the network command in BGP, but not quite in the same fashion as we did with OSPF and with EIGRP. The command is going to look much the same, but there's a little nit to pick here, because where IGPs identify the interfaces to be enabled with the protocol in question, BGP uses this command to identify the networks to actually be advertised by BGP. Now, the network specified by the BGP network command has to be an exact match for a network contained in the IP routing table, and that includes the mask, should you include it. Because using the mask in the BGP network command, it's not required. It is highly recommended though. If you're called upon to troubleshoot a BGP config, even if it's yours, and that config is missing the masks on the network statements, that's the first thing I would check out. That is very likely the issue. You got to use the mask or you'll end up only with the classful networks, or you'll end up with no networks at all. And I have a feeling we're going to see that live as well. Now we're going to get this lab started. We're going to use the same adjacencies that we just built, and we're still using the loopbacks. And what we'll do first is advertise R3's loopback via BGP. So let's bring our live equipment up, and we will do just that. And we're going to use the network command here, and network number is the only option. So actually we'll go with 3333. And backdoor route, that's more of a CCIE level topic. We're going to leave that alone for right now. Route map, we're going to leave alone for right now to modify attributes because we haven't even covered what attributes are yet. So that kind of leaves us with mask. But do note that there is a CR here. So this is a legal command that I really recommend you put the masks in. And so does Cisco. So we'll go with the 32-bit mask because that's what we put on our loopback. And it won't surprise you that we've got some options there, and they should look familiar, backdoor and route map, but we're going to leave those alone for right now and just go with that. So what should we do now? We should go over to router 1 and see what we have for a route. And this is a new command. This is one you're going to come back to time and time again as well, and that's show IP BGP. And notice it gives you what the local RID is, and now these status codes. And we've got some origin codes there, I for IGP, E for EGP, and a question mark for incomplete. And the origin, that's an attribute, and that's actually the first attribute we're going to talk about later in this particular video. Status codes, suppressed, damped, history, and then we've got valid and best. And that's a phrase you should get used to. And of course, the last one you see there is I for internal, because that's what we're looking for. We're not going to send pings around here because that's not a true test of BGP connectivity. What we're looking for with BGP is what we call valid and best. And that's what we have to the left of that network 3333 entry. And just to extra highlight it there, we've got valid and best. It is not enough to have an asterisk next to the route. It is not enough to have the greater than sign, or what I prefer to call an arrowhead, because I call it an asterisk and arrowhead. I think that's a great way to remember it, especially if you're new to BGP. You've got to have an asterisk and an arrowhead next to that route for that to be the valid and best route. Because as we'll see in upcoming labs, and of course we want redundancy, right? If this path to 3333 goes down, we really want to have another one. Well, when BGP has multiple paths to choose from, it's going to pick one as valid and best, and it may mark the others as one or the other, but again, you got to have both. You got to have valid and best. So far we're good here. We've got our network entry, we have our next top IP address, there's a metric of 0. We're going to be coming up on how to work with that metric and something called a lock perf. And that is actually short for local preference. That's another BGP attribute we'll be working with here in this section. And wait is another BGP attribute we'll be working with in this section. And the path, you'll note 200 and then I. That's what we call the AS path. And that's another attribute. So like I said, we're going to be coming back to show IP BGP here pretty darn often. Right now, let's go over to router 3 and have a look at what this table looks like, what this router's BGP table looks like. And you'll notice that we still have a valid and best, but a couple things to note here. We have some different status codes because we have a slightly different version here. I wanted you to get used to seeing more than one. Also note we do have valid and best next to that network entry. The next hop is all zeros because we're on the router that actually has this network on it. So there really is no next hop. And I'm sure a couple of you noticed that there's no number in the AS path, just the letter I, and there's a weight of 32,768. And you can see on the screen the router 1 part is gone, but we know that's router 1 show IP BGP at the top. And you'll notice the weight there is 0. That might just come up in our discussion of the weight attribute, but it's a good thing to note right now. Let's see what happens though if the network command doesn't quite match what the IP routing table has. And to do that, we'll go ahead and just create another loopback. And we'll call this one loopback 33, IP address 33333. And I'm going to put a 24-bit mask on it instead. But let's say then under router BGP 200, I put there we go, I knew I could do it. And a full mask, 32-bit mask. Well, when you hit enter, you're not going to get an error message. You know how I've said in a couple of courses, especially if you took the CCNA with me, I'll say, you know, it's great because most of the time, 99% of the time, when something is a little amiss, the Cisco router or switch is going to give you a little hint or a little console message. Well, here we're not getting anything. But what we might get over on router 1 is a lot of nothing as well, because we don't have an entry for 33333 because that network statement is actually incorrect over on router 3. But when you put an incorrect network statement in, the router is not going to say anything to you. The router is going to say, well, that must have been what that person meant to put in there. So let's take that entry out. We'll do a Control A to move to the front of that line. Now, if I try this, I want you to see this message as well. Yeah, you'll get this and say, you know, BGP, it's a BGP specific message, incorrect network or mask prefix link configured. And you're like, what? Huh? Well, if you put a 24-bit mask here, of course, your entry needs to be 33330. And now, let's see what we have over on router 1. And we already have that entry. And again, it's valid and best. Exact same entries for the next hop, metric, local pref, wait, and path. And it makes sense because it's a path coming from the exact same router. So we've looked at the network command, and we are going to be looking at it a lot here in this part of the course, of course. But let's go ahead and start talking about BGP attributes. I want to give you just a little bit of theory here, and then believe me, we're jumping right in. And with BGP attributes, if this did not come up on the route exam, it's going to come up on your CCIE written, it's going to come up on something. So I would have these down cold, because these are the BGP path attributes we're going to start with. We have well-known mandatory attributes. We have well-known discretionary attributes. We have optional transitive attributes. And then finally we have the optional non-transitive attribute. Oh, that's a lot. That's a lot to remember. But again, we're going to see just about every one of these in action in the course, and they will become second nature to you that way. The well-known mandatory attributes, we're going to see those throughout every lab we do. And we did just see these three in our show IP BGP table. The well-known mandatory attributes being AS path, origin, and next hop. The well-known discretionary attributes are local preference, local pref, or as we saw, LOCPRF, LOCPRF, and something called the atomic aggregate. Sounds dangerous, right? Like the ultimate nullifier, but it's safe, I promise you. No need for any goggles or anything like that. The optional transitive attributes are aggregator and community, and that optional non-transitive attribute, the MED, the multi-exit discriminator. It's hard not to say that on the Marvin the Martian voice, isn't it? The multi-exit discriminator. So we've got these three mandatory attributes. They are going to appear in all of our BGP update messages that go out to neighbors. These are the only three attributes that a BGP speaker has to understand, because not every BGP speaker you deal with is going to understand every BGP attribute. It doesn't work that way, unfortunately. Now, the optional attributes, they can be a bit of a pain in the butt when it comes to BGP, because again, not every BGP speaker is going to understand every optional attribute. And that's where the difference between optional transitive and optional non-transitive comes into play. A BGP path that's carrying an unrecognized transitive optional attribute will be accepted, and should that path be advertised to neighbors, the partial bit will be set and the attribute advertised to the neighbor. Now, marking an attribute is partial is really the equivalent of the advertising router saying, hey, I didn't understand this, but maybe you will, so here it is. An unrecognized non-transitive optional attribute will not be passed on to other BGP speakers. And of course, the key there is non-transitive. It's not going to transit from one AS to another or even between speakers. With that said, and I know that's a little complicated there at the end, especially if BGP attributes are next to you or new to you, but it's really all going to become second nature to you with these labs, and we're going to start examining the individual attributes at the beginning of the next video. See you there. We're going to start our look at BGP attributes with a look at two attributes we discussed very briefly in previous videos. The first one being the origin attribute. You're going to see this attribute at the far right of the output of show IP BGP. Next to the number under path, you'll see the couple of letters I there. And by the way, I've set up another lab, so these routes are gone from the live equipment, so I'm bringing them to you on the board right now. We will be back on the live equipment very soon. Now, the actual origin codes are shown as well in the little origin codes row under show IP BGP. I would definitely have these down cold for the CCNP exams, and they're very straightforward, nothing confusing here. You either for the origin code have an I indicating an IGP via the network command, and that's how we got those two routes in there. E for EGP, that indicates a path that originated from an external gateway protocol. And question mark for incomplete, that's not as self-explanatory in iOS help. What that means is the true origin of the route is unclear because it was learned via route redistribution. Now in the best path selection process, it's I over E over question mark. Internal route is, IGP is preferred for source over EGP, and in turn EGP is preferred over an unknown source. So much more about this process later in this section. And by golly, look at this, it's later in this section. We're going to talk about the best path selection process here and the AS path attribute, which we saw briefly in the other video. The name is the recipe. It shows us the autonomous systems along the path to the destination network, including the AS the destination network resides in. The shorter the path, the more preferred the path during that best path selection process. The main purpose for the AS path attribute's existence is to help prevent routing loops, which we are always trying to prevent. And the way that works, if a BGP speaking router receives an update that has its own AS number in the path to a destination, the speaker says, something's wrong here, and that particular route is going to be discarded. Now in this example, and this was router 1 in our previous lab, the only AS shown in the path is the AS containing the networks, because the AS was right next to router 1, and you see under path 200, and it's followed by the origin code. On router 3, which was the router that actually contained those two networks, as we go down here you can see the only thing under the path was literally the letter I. Now we're going to run a lab that allows us to see the best path selection process in action. And I have pre-configured this lab. I'm going to show you why in just a moment, but they're all commands that we've used to this point. I know you know how to check adjacencies and to create those peerings, and I know that you know how to use the network command. So when you see everything I did here, you're going to see why I didn't show it on video. Now, first I'm going to show you the physical network setup. And for the sake of clarity and sanity of everyone involved, I'm not going to show you the physical interfaces and the switches in the BGP diagrams, because these get pretty detailed and we don't need the extra drawings in there. And I strongly suggest you write this network out, and I'll show you the full network, physical network there in a moment. I know it's not all on screen, but I want to point out the networks to you. Routers 1 and 5 share an Ethernet segment 10.110/24. Routers 1, 2, and 3, the serial connection that we are so used to at this point, 172.12.123.0/24. And then finally, routers 2, 3, and 4 also share an Ethernet segment 172.12.234.0/24. I see we have an extra 0 in there. I'll get rid of that. And I urge you to write this one out, because we're really going to be tracing some IP addresses and seeing why certain routes aren't going in the BGP tables, that kind of thing. So it's very important that you know exactly where all the IP addresses are. And of course, as always, I'm going to say it anyway though, the router number is always the last octet. I know you know that, but I'm telling you anyway. So go ahead and pause the vid if you need to and draw that out. And meanwhile, let me show you what I have already built. And with this many adjacencies and everything else, again, you know the network command, you know the peering command, the neighbor command, and you also know how to verify. So I didn't want to show you all that because we've got plenty of other stuff to show you, believe me. But you can see the only routers that share an adjacency inside an AS, an internal adjacency, are routers 1 and 2. And routers 3, 4, and 5 are in their own ASs. I've created a loopback on each one with the router number for each octet, and I have already advertised them into BGP. So at this point, router 1 has at least one entry for every loopback in our network. That should be true of every router, but it'll have multiple paths for the loopbacks on routers 3 and 4. And that makes sense because router 1, to get to, say, router 3's loopback, it could go either directly to router 3 through its eBGP adjacency, or it could go down through 2 and then over to 3, and it could even go to 2 and then 4 and then 3. It's always nice to have redundancy. And to get to router 4's loopback, router 1 could either go straight through 3, or it could go down to 2 and then down to 4. So it sounds like we've got some path decisions to make. And let's go ahead and bring up the live equipment. And what are we looking for next to the routes? We're looking for valid and best. And now you see why, because in the previous labs, we didn't have any multiple entries for any routes. And you can see here with show IP BGP, it's getting a little more complex, got a few more IP addresses thrown in there. And you can see router 1 has one entry for its own loopback, makes sense. And the next hop is all zeros, which also makes sense. It has one entry for router 5's loopback, also makes sense given the topology of the network. It only has one way to get there. And router 2, the next hop is 123.2, makes sense, that's the direct path. But we notice for 3 and for 4 that it has two entries. And you probably notice a couple of other little things over there, like some numbers that are there under a certain column and then not there. And that's particularly true of 123.3. It's not showing its metric, which should be 0. But under local pref, that's what I'm really concentrating on here. We see some entries that have nothing and some entries that have 100. But this is what we're particularly interested in right now, are these entries for 3 and for 4. And we see a valid and best. You can see here for 3333, the router has two entries, and it's chosen the path with 123.3 as the next hop IP address as the best and valid path. And for the entries for router 4's loopback, it's chosen, again, the path through 123.3. So watch those because, your eye can play tricks on you. I like to highlight them whenever I can and just say, okay, here's valid and best, because it's easy to think the first entry for the path is going to be valid and best. It's real easy, but that's not always the case. As you see here, it is the case with 4444, and then the path that wasn't chosen is under it. But here, the valid and best for 3333 is actually this one. So why? Why was this? Why were those particular paths chosen? Well, when deciding between multiple paths for the same destination, we have a pretty long-winded decision-making process. This is not 1 or 2 steps. And I would just have this memorized down cold for your exams. It's a very good idea. And here is that list. First off, the highest weight is always preferred. BGP weight, by the way, is a Cisco proprietary attribute. So the highest weight is going to be preferred. Then, if that's a tie, or there are non-Cisco routers involved, the highest local preference, that LOCPERF, that's preferred. If that's a tie, then the locally originated path is preferred. If that's a tie, then the shortest AS path is preferred. I'm not going to keep saying that's a tie, but I will say next up in the tie-breaking process is the best origin code. And by best, we mean I, then E, then question mark. The next one is the lowest MED, the multi-exit discriminator. And I know we haven't gotten to that yet, but we will. 7th step is an eBGP path will be preferred over an iBGP path. then its lowest IGP metric to the BGP next hop address. As you can see, we're getting a little desperate here. I shouldn't say we're getting desperate as much as we're getting really, really detailed, because you're not going to see that many situations where the tie is all the way in the 8th or 9th or 10th step. But that 9th step being the oldest path, and the 10th step is being the path from the BGP router with the lowest BGP red. So finally, we find a purpose for the BGP red. Now, with that list in mind, on the next video, we're going to closely examine those selections that were made for the paths to router 3 and 4's loopbacks, because this really will turn a light bulb on for you. It's really going to illuminate some selections and some things that get done in labs after this. So take a deep breath. I know there's a lot of info in this one, and we're going to dive right in at the beginning of the next video and start looking at this path selection process in action. Hey everybody, Chris Bryant here. Thanks for dropping by and taking a look at my free CCNA security course here on Udemy. Totally updated for the latest version of the exam, the 210-260 exam, all about virtual private networks. And not only is this course going to come in handy in the real world, it's really going to help you on your CCNA security exam, because configuring and troubleshooting VPNs is going to be a huge part of your CCNA security exam. And this totally ad-free course is going to get you ready for success with VPNs on your security exam day, and also working with VPNs in real-world networking situations, because in the end, that's what it's all about. By the way, this course assumes no prior knowledge or configurations of VPNs. If you've never touched one, you've never seen the terminology, you're actually in the right place, because I'm going to take care of that for you. Because for that security exam, the first thing we have to do is get the theory down cold. The labs are great and there's plenty of lab work here, but we've got to tackle a bit of theory first. And we're going to talk about why we would use VPNs in the first place, and then compare authentication header and encapsulating security payload. Quite the mouthful, AH and ESP. We're going to talk about the similarities and differences between the two, and when to pick one over the other during a live config here in the course. Now, if you don't even know what those are, no worries, because I'm going to take care of that for you as well. We're going to go over all of the main steps in VPN creation, in theory, and then during a live lab on live Cisco routers. I'm going to give you a VPN success checklist that guarantees you get every step right every single time, because there are quite a few steps here, and you got to do them in order, and then you got to get them all right. And that's just what we're going to do here. We're going to go over IKE policy creation, application, and of course verifying. Something called a transport set with VPNs. We're going to create those. I'm going to explain them to you clearly, and we'll see how to apply them. And another kind of access list, a crypto access list, how to configure it and how to apply it. This gets tricky for a lot of people because they don't know a couple of simple success rules. But at the end of this free course, you will, and you will nail it on exam day. And by the way, even when you're done with that course, this course never stands still, because at least once a week, I'm going to add a new security training video from my YouTube channel, including video practice exams, 5-minute video boot camps, and video flashcard exams. All brand new videos created for the latest version of the CCNA security exam. This all starts August 10th. That's when I'll post the first new videos in the VPN course. They'll all be up by Monday, August 15th. So if you join now, you'll be automatically notified when new videos are up. And actually, once you join after that date, you'll still be notified when those new security videos are put up from my YouTube channel. I'm Chris Bryant. Thanks for taking 3 minutes with me here, and I look forward to teaching you all about VPNs. We are about to dive headfirst into the wonderful world of virtual private networking. Before we jump on some labs, though, we've got to go through some theory and go see exactly what's going on with some of this new terminology, because it's going to be new to you, of course. If you haven't seen VPNs before, it's going to take you a little while to absorb it. There's nothing wrong with that. That's all part of the learning process. But if you are new to VPNs, please spend a little extra time with this video. Watch it a couple of times before you move on to the labs, because the labs will be that much more helpful that way. Speaking of theory, the first question I have, maybe the first question you have, is why we VPN in the first place. And the reason is that, the shared channels that we generally use between routers, between WANs or over our WANs, they have a major drawback. They're shared. And if something is shared, what does that mean when it comes to privacy? privacy may not be the best. It also may not be terribly secure. So I'm sure you already see where this discussion is going. But before we proceed with that, remind me from your CCNA studies, if shared channels aren't exactly private and aren't the most secure things in the world, why do we have them? Cost, because they're cheaper. And we can't have VPNs between every endpoint in the world, but sometimes we've got routers and communications that need to be a little more private than we've got a chance to have over a shared channel. And one of the great things about these virtual private networks is that we bring the privacy to a shared channel because we're actually tunneling through the shared channel. We are digging, if you will, a secure channel or a tunnel through the shared channel. And another great thing about VPNs is that we can apply rules and policies to the virtual tunnel without applying them to the physical channel we're tunneling through. So that is a great feature of VPNs. Three more great features of them is these three features that they bring: data origin authentication, encryption, and data integrity. And I know these are awfully self-explanatory, especially the first one, but I want to draw a clear line between these three. Data origin authentication is done on the recipient end, and it allows the recipient to guarantee the source of the packet. Because we know that all kinds of nasty things can happen along that dotted line, right? That VPN. We could have a man-in-the-middle attack, and they grab some packets and they do some nastiness. So router 3's got to be able to say, okay, did this packet really come from the source IP address that's indicated on the incoming packet? Now encryption, we know all about that. We know what's going on here. Encryption makes the contents of the packets unreadable during transmission. So even if that man-in-the-middle attack occurs or someone intercepts them in another fashion, then the packets are essentially useless to them. It's like going to the library, stealing a book, and it's written in a language you can't read. Don't steal books from the library. Integrity. Now integrity, that is also done on the recipient's end, and that is the recipient's ability to ensure that the contents of the incoming packet were not tampered with during transmission. And basically router 3 here is getting a packet and saying, hey, does this packet say what it said when it left the original sender? So these are three great features to have. Now that tunnel, it just doesn't build itself. You and I have to do a little building here. And we used to use a little something called the generic routing encapsulation. I love that name. What do you want to call it? I don't know. It's pretty plain. Just call it generic. Well, it was fine for a long time, but there was just one little drawback. GRE is so generic, it does not allow for an encryption scheme. And you read that right, and you heard that right. GRE does not allow encryption, and that's a little too generic for today's world, in my humble opinion, and I'm sure you agree with me. Now, GRE's made a little bit of a comeback. We may talk about elsewhere working with IPsec, but it's definitely not working by itself. And this whopping GRE security hole is corrected by IP security, which is usually shortened to IPsec in VPN discussions and anywhere else. You're almost always going to see it just called IPsec. Now, thankfully, IPsec brings encryption and authentication to the table, and it is a combination of these three things, and I'm not presenting them to you in any particular order, but you should know what these three things are. The first one, authentication header, usually referred to as AH or IP Protocol 51 or just Protocol 51. I think you should know the AH and ESP numbers because I've seen Cisco documentation and some non-Cisco VPN material that make a lot of references just to the numbers. So AH, it defines a method for authenticating and securing data. But I think there's a word missing from there. Now, authentication header, as we'll see, I've got some visuals coming up for you, but AH is literally a header. There's no encapsulating going on, which brings us to, clever segue, the encapsulating security payload, ESP IP Protocol 50. Now this defines a method for authenticating, securing, and encrypting data. Now the Internet Key Exchange, the IKE, we're going to be working with a lot of IKE policies live here in the next couple of videos. So this is definitely one we need to know what's going on. And simply it negotiates the security parameters and the authentication keys that are going to be in use. Let's take a few minutes here to talk about AH and ESP and compare the two. Now, AH brings perfectly good security to the table. There's data origin authentication, there's optional anti-replay protection, and AH does not fully protect the IP header info, but it does protect the payload. And you'll see why it doesn't fully protect the IP header info in an illustration in just a moment. But
the thing is with AH, and I repeat it here, it offers data origin authentication. It does offer integrity, but it does not bring data confidentiality, which is a huge difference when you're comparing it to ESP. Basically, AH lets us know the packet's indicated source is indeed the source. It lets us know the packet's contents were not changed during transmission, but it doesn't guarantee that somebody didn't read it along the way. So it does have that lack of data confidentiality. Now, ESP just brings everything we could ever want. Data origin authentication, data confidentiality, anti-replay protection, encrypts the data. It's fantastic. So again, I'm repeating it there, but it does bring us that data confidentiality that we lack when we use authentication header. So the musical question, why would we ever use AH instead of ESP? Why would we do that? This should remind you of a discussion we had during your CCNP studies, your early CCNA work. Two protocols, one of them had a ton of features like windowing and sequence numbers, and the other one didn't have jack. And of course there I'm talking about TCP and UDP respectively. UDP didn't have any of the great features that TCP had, but we use UDP every day for all kinds of things in our networks. And why did we do that? Overhead. And that is one of the reasons that you would choose AH over ESP, is that AH has much less overhead than ESP does. ESP is much more processor intensive than AH. The actual encapsulation and de-encapsulation itself, is a lot of extra work for the router that it doesn't have with AH. There's another reason though. ESP requires what we call strong cryptography. And that is not available everywhere. It's certainly not available on every Cisco device or every non-Cisco device. And it's not even allowed everywhere. It's actually illegal to have certain devices that have strong cryptography in certain parts of the world. And when you start up a device that has strong cryptography, it'll actually have a warning for you beyond the usual copyright notices, that kind of thing. And it'll say, hey, there are places in the world you're not allowed to use this. And if you have any thought that you're in one of those countries or you want to check the list, here's the URL to check the list. So they're very, very careful about telling you that. But that is another reason you might have to use ESP. Now, let's go ahead, take a deep breath, because we're going to hit tunnel and transport mode here for a few minutes. And what you've got to do here is decide between these two modes whether you're running AH or ESP. Now, tunnel mode, that's our default mode. And with this mode, the entire IPsec process is transparent to the end host. Now, the VPN devices, which are the routers in our case, in our labs upcoming, they have a lot to do. Tunnel mode protects the entire packet by doing all of these things. The packet payload is encrypted. If you use ESP, you're going to see a header and a trailer attached to the original IP header and the data. And I have an illustration for you in a moment, I promise. And what we're doing there is encapsulating the original packet. That's where the E comes from in ESP. Now, if you're using AH, a header is inserted, but there's no actual encapsulation. And finally, with this mode, a new IP header is attached, and it's going to reference tunnel endpoint IP addresses. So in a way, you're disguising the original IP addresses that are in the original header by the encapsulation and also just by putting tunnel endpoint addresses on that header. Now, here's a visual that will really help you knock all that theory down. Now, ESP with tunnel mode at the top, you see we've got the header and the trailer there encapsulating the original IP header and the data payload. And you've got that new IP header on the very front. Now, AH with tunnel mode, you see the authentication header, the AH, is inserted right in front of the IP header, and there is a new IP header put on as well with the tunnel endpoint addresses. Now, ESP and AH combination with tunnel mode, you can run ESP and AH. They are not mutually exclusive. And if you do that, you see where everything is. The authentication header is put right in front of the original IP header. Then the AH, the original IP header, and the data payload are encapsulated by ESP. And then you've got that new IP header put on the very front. Whew. A lot going on there. So then finally, after all that's done, the entire IPsec protected packet is sent to the remote VPN device. And of course, that device has to unencrypt and de-encapsulate the packet and then send the original packet to its intended destination. Whew. So you can see there's a lot going on there. So that sounds like a lot of overhead. And transport mode brings us that now familiar, overhead versus protection level argument, because transport mode is going to encrypt only the IP payload. It's going to leave the IP header alone. And it's a bit of an oddity here. You will still have an outside IP header, but it's just going to be a copy of the original header. And that's whether you choose ESP or AH. And this is what we're looking at. You see ESP with transport mode. We've got the header, we got the payload, we got that encapsulated with the header and the trailer. But in the front, we have a copy of the original IP header. And with the authentication header with transport mode, the AH is put right in front of the original IP header, and then a copy of that original IP header is put on the front. So this is not as secure because you're not disguising the original IP header addresses in any way. So somebody can pick those off and start getting a little information just from there. So again, the argument here is overhead. And that's just really, that's what it comes down to. That's what it comes down to really with AH and ESP in many cases. And when it comes to tunnel and transport mode, you've got to make that decision about, overhead versus protection level. I think that is enough theory for right now. Great stuff there, and we're going to start putting some of it into action in the next couple of videos, build some IKE policies, and I'm going to give you that success checklist. I got a 5-part VPN success checklist for you that I want you to memorize, use it on the exam, and then use it in the real world, because I'll tell you, here's a real world note. Here's the thank you for making it to the end of this video. I don't mean it, that was boring, but I know it's 13 minutes of theory. I know that's a lot of theory. So here's your bonus for making it all the way through. I'll tell you the number one thing that causes problems when you're configuring VPNs at the command line the way we're going to do. It's just forgetting a step, because you've got a couple of different policies that have to be negotiated. You got to create something called a transform set. It's not that complicated. Don't let it worry you. Then you've got a crypto access list, which sounds like something you're going to write in another language, but it's the same kind of ACL that you've always written, just applied in a slightly different way. You just got a lot of stuff going on. So I'm going to give you this checklist at the beginning of the next video, or near it anyway, and when we start building it, we'll just check off one thing at a time, because when you have an organized plan to build something like a VPN, you are way ahead of somebody who just says, okay, I'll just sit down with the router and knock it out, because I guarantee you they could spend 15 minutes configuring and an hour and a half troubleshooting. With all that said, thanks for listening, and I will see you on the next video. We are almost there. We're just about to create our first IPsec VPN. There are 5 overall steps to this build, and a quick word to the whys here. If this is your introduction to VPN terminology, or it's been a while and you're a little rusty, don't let it intimidate you. It just takes a little getting used to, because we've got 2 policies to build. We've got a crypto access list to write. We got a couple of other things we got to do. So a lot of little details here, which is why I like to have a checklist in mind when I'm going to write one or troubleshoot one. And the first step of the VPN build is the process initialization. And we don't want just any traffic triggering a VPN build, or we're going to have a lot of VPNs, we're going to have a lot of overhead. So what we're going to do is write a crypto access list to define what we call interesting traffic. That's the traffic that will actually signal to the VPN device, in this case a couple of Cisco routers, that it is indeed time to get to work. I do not choose to configure the crypto ACL first. This is the first step in the build, but I like to get my policies taken care of first. That's the order we're going to take this in. So we're coming back to the crypto ACLs. Be sure you have these 2 phases totally clear in your mind as to what goes where and what's going on with IKE Phase 1 and IKE Phase 2. They're both negotiations. The first one, this is where the, take a deep breath, Internet Key Exchange Security Association is negotiated. And that's what we call an IKE SA, and that's what we'll be calling it from here on out. When this phase is successful, the result is one bidirectional IKE SA. As opposed to what we get at the end of IKE Phase 2, there is a negotiation here, but what we're negotiating here is the IPsec Security Association. So if you say it out loud, it's all the way, it's IP Security Association. Let's just call it IPsec SA. And when Phase 2 is successful, what we end up with is 2 separate unidirectional IPsec SAs. Now, of course, the big thing to be concerned with here is if Phase 1 is not successful, there is no Phase 2. So we got to watch our P's and Q's when it comes to that Phase 1. Now, finally, and just popped up on the screen there, the data transfer is our middle section, and that's where the data is transferred, but you knew that. So we've got the VPN built, we've got our policies negotiated, we have the actual exchange of data, and then we got to tear that VPN down, because once it's no longer in use, we don't want to spend the overhead, we don't want to use the overhead to keep it up. Now, we can configure the tunnel to be torn down at a couple of different times, one of them being when a certain amount of data has gone through. You can also configure it to be torn down after the tunnel has been idle for a given amount of time. We'll see both options here shortly. Now, of course, the first question I had when I read about this the first time was, well, what happens if I'm sending traffic through the tunnel and the tunnel's supposed to be torn down? That doesn't sound good. Well, what can happen and what will happen there is that a new SA can and will be negotiated on the fly while the existing SA is still in place. So we're still in good shape if that's what happens. Now we're going to get to the fun stuff. We're going to start configuring. And in this lab, we're going to build a VPN between routers 1 and 3. There's a shared channel between them, frame relay to be exact. And just to show you here, let me go ahead and slide that over a bit. I will send a ping over to 172.12.123.3. Now that's slightly off the screen. I will bring that up. And we're in good shape. So we're using the 172.12.123.0/24 subnet, routers 1 and 3 communicating over frame, no problem at all. And we're going to concentrate our config, or get started actually, on router 1 with these 5 values. And as we go along, we're also going to discuss why you would pick certain ones here of encryption and the hash choices we're given, and also why you might not want to choose others. And also, I will upload a Cisco document. Instead of giving you the link, I'd rather give you the document because the links change. It's some information that's the source for the information you're going to see here, and it's well worth your time perusing it before you take your CCNA security exam. So let's dive right in. With authentication, we're going to do pre-shared keys. With encryption, we're going to do something called 3DES. Every once in a while, you'll see this called TDES for triple DES, but generally it's 3DES. Hash, we're going to use something called SHA, which I like to pronounce SHA. Lifetime, 24 hours. That's the config we're going to put on router 1. That's how long we'd like our phase 1 IKE SA to last. And something called the Diffie-Hellman group. We're going to go with group number 5 here. Let's go ahead and bring up the live equipment, because first things first here, we have to make sure that everything is on that should be on. So let's run a little command, our first show command, show crypto ISACMP. And you better get used to this one, because this is the show command, obviously, for our phase 1 info. And what we're going to do is go with policy. And you might say, well, hey, we haven't configured anything yet. Well, we haven't, but there will be a default protection suite here on the router or your VPN device. And there's your default protection suite. We have not configured one yet. And you see a value for each one of the 5 categories I mentioned: encryption, hash, the authentication method, the Diffie-Hellman group, and the lifetime. Notice the lifetime mentions seconds and no volume limit. Remember that. It's good stuff to know. What we want to do, though, is configure a policy that goes along with the values that we had on the board. And let's go back to that. Pre-shared keys, 3DES, SHA for the hash, 24-hour lifetime, and a Diffie-Hellman group of 5. So since that does not match up what we've got here, we've got to create our own policy. That's what we want to do anyway. So the command for that is crypto ISACMP policy. And then we're going to put the priority of the protection suite. I'm going to address what these priorities mean and when they come into play, but note that you have to assign one. There's no option for don't give it a priority. It's got to have one. And we drop into ISACMP policy configuration mode, and now we'll look at our options from there. And you can see it even mentions to us, pardon me, the ISACMP commands. That's nice. So we've got authentication, we've got encryption, group hash, and lifetime. So they're all there, along with the other usual suspects of default, exit, and no. Let's look at our options for authentication first. And we've got a couple of RSA options here. What we're going to do for this lab is you use pre-shared keys. And you'll notice there's no option there. So that's great. We're going to have pre-shared keys. Where are they? Where do we set them? That's coming up. We have to use a separate command for that. Now we're going to choose our encryption. And here we have a 3DES, which is what we said we wanted to use. We have an AES and DES, Data Encryption Standard. Let's go back to the board for a moment because I want to discuss those three with you and what Cisco has to say about them. And also you'll see this information in the PDF that I left for you. DES, it's easy on your router resources, but this is a very big but. It is the least secure of the three. It was fine in its time, but it is no longer considered secure, and Cisco actually recommends that you actively avoid its use. Now, 3DES or triple DES, it's very similar to DES in operation, but as you'd expect from the name, a block of data is going to be processed 3 times rather than once. And the word generally used to describe 3DES level encryption is adequate. It's okay. It's not great, but it's okay. Now, AES can be really great. The Advanced Encryption Standard, it's much stronger overall security than either one of the other two choices, but also it requires an iOS later than 12.3T to run AES, which in today's network shouldn't be any issue for you, either lab or production. But we're going to stick with 3DES here. Now, I want to bring a couple of terms to your attention that, again, I say this often, you need to have these crystal clear in your head, which is which. Now, all three of these are what we call symmetric encryption algorithms because they use a single key that performs both encryption and decryption. That's opposed to asymmetric encryption algorithms, which use 2 keys, a public key and a private key, the public key used for encryption and the private key for decryption. So with all of that in mind, we are going to go with 3DES here. And what else do we have? The hash choices. Officially, the full word is hash. I put has, so that was fine. Now we have that secure hash standard, SHA. And we have our old friend MD5. Remember MD5 from your CCNA studies? It's really one of the first encryption algorithms you run into. And not to badmouth MD5 right in front of it because I know it's sitting right there, but I mentioned this in your CCNA studies, so I'm going to mention it again here, and Cisco does as well in their documentation. You got to watch the use of MD5 because especially the version of it that is used to encrypt passwords in your config, when you run that certain command, remember service password encryption, well, that uses MD5. And what it's really good for is very casual attacks, or I should say defending against very casual attacks. MD5 is easily crackable. That's not just me talking. Cisco will tell you that. Their version of MD5 on the routers, you can pop it. You can find a program to pop it loose in less than 30 seconds, probably less than 5 if you know where to look. And so the problem is with MD5, of course, is not particularly secure, obviously. It's good to prevent what we call the over-the-shoulder network attack. When someone's in your room, your server room that shouldn't be there, and they look over your shoulder and say, oh, his password is CCNA. Well, it's good to prevent that, but that's about all I would really depend on it for. So here, we're going to take SHA. Now, with Diffie-Hellman group, my fault. With the Diffie-Hellman group, you're actually going to use the command group because as you saw, there was no Diffie-Hellman option when we looked at our options a few minutes ago. So here, different devices are going to have different capabilities here. And we would prefer a higher Diffie-Hellman group number than 5, but this is the highest this particular device is going to handle, so we're going to go with that. And the higher the number, the larger the modulus, and it is considered more and more secure. As a matter of fact, I think Cisco tells you really not to use group 1, even though it's still widely available. So let's go ahead and go with group 5 there. And lifetime. Now, I gave you a spoiler on this earlier. On the board, I broke it down into seconds for you. But let's say I came up to you and said, hey, I know you just got your CCNA security certification by taking Chris Bryant's class. I need you to set write the policy, and I need you to set the lifetime of it to 24 hours. That's a great job interview question. Someone comes in, just see if they know what they're talking about. Hey, write me an IKE Phase 1 policy. And if I asked you to write lifetime for 24 hours, what would you put right here? We're going to talk about that and continue this lab at the beginning of the very next video. We're almost exactly where we were at the end of the previous video. Yours truly hit an extra key, so we got a little bit of an extra screen, but we are now at the same place. In that IKE Phase 1 policy, we've set authentication, hash, the encryption, and the group number. Now we got to set that lifetime. What's the first thing you ought to do, not just here really, but with any command that has any unit of data that it's going to use, or especially units of time? And that is use iOS help, because some commands are going to use seconds, some time-based commands will use minutes, some will use hours, some will use a combination thereof, and you don't want to enter one number thinking it's seconds when actually it's hours. Now here, if I asked you in a job interview situation or on a practice exam, enter the value that's going to give me a 24-hour lifetime. Well, if I enter 24 here, iOS help wouldn't let me do that anyway. And then you go, and then you run iOS help to see what's going on. The iOS would not allow you to put that value in because the range is 60 to 86,400. But what if I asked you, hey, put in a lifetime of 80 hours? And you put in lifetime 80 thinking that was hours instead of seconds just because you didn't look in iOS help. Just save yourself a lot of trouble and use iOS help to double check, especially your time-based values, but your database values as well. So let's go with the actual default and the maximum, which is 86,400, which is also 24 hours. So we've got our lifetime set up. We need to verify that we wrote our policy correctly. And we're going to use that command we saw earlier when we had only the default, show crypto ISACENP policy. And now all of a sudden we have two policies, which is a good thing because we just wrote that top one. Protection Suite of Priority 100. Sounds kind of formal. Well, we've got our encryption algorithm, our hash algorithm, authentication method, our Diffie-Hellman group, and our lifetime. You can just check them all right there just to verify that you entered indeed what you thought you entered. Now, I've gone ahead and pre-configured Router 3's policy. I usually don't do that, but you've seen the commands here in this video and the last one. We don't need to walk through that again, but I want to ask you a question actually about that as I remind you about what's going on with the policies or fill you in on it the first time actually. This policy is the heart of IKE Phase 1. Now, when Router 1 initiates the communication, which is what we're going to do eventually, these policies are going to be sent over to R3, the IKE Phase 1 policies, the ISACENP policies, the ones we just saw. And you can see Router 3 saying to itself, let me see if I have a match for one of those. So what happens then is that Router 3 looks among its own policies for one matching the policy coming in from R1. Now, the lowest numbered policy will be checked first. That's where the numbers come in. If that lowest numbered policy doesn't match, the next lowest numbered policy is checked, and so forth. Now, if a match is found, we proceed to Phase 2. If no match is found, there is no IKE Phase 2. Now, I'm going to show you on the board the config that I put on Router 3, and I gave you a couple of huge hints here. First, I italicized near because it's a near match for policy 100 on Router 1, the one we just wrote. Is near going to be good enough? And I know you could spot it on your own, but I even bolded the one that's different. So authentication, encryption, hash, group, those are all exact matches for policy 100 over on Router 1. What about this lifetime though? I set that to actually half, 43,200 seconds. We get so used to values having to match exactly in networking because frankly in networking values often have to match for anything really to happen. Whether it's OSPF hello and dead timers, some BGP values, all kinds of things, they have to match. PPP, if you configure PPP, you can't have a near password match. That's not going to work out. With OSPF, as I mentioned, if the hello and dead times are different between two potential neighbors, they will stay potential neighbors. They will never form an adjacency. So I'm hammering you over the head with this for a reason, and here's why. With IKE Phase 1 policies, the hash, the encryption, the authentication, the Diffie-Hellman group, that number, they have to match. They have to be an exact match. But lifetime does not have to match. What it has to do, though, is this. The recipient policy lifetime may be equal to or less than the lifetime of the incoming policy. And should the recipient policy lifetime be less than that of the incoming policy, the lower value is used. Boy, that's a good practice exam question. Good job interview question. So you got to know not only that the lifetimes don't have to match, but on the recipient end, it has to be equal to or less than the lifetime of the incoming policy. Then you got to know that the value that will actually be used is the lower value. So there is a lot going on there with our policies. That is going to wrap up our IKE Phase 1 config. So coming up next, we're going to get that IPsec SA configured, set our values for that, and then we'll march on to our crypto ACLs. I'll see you on the next vid. When you're running a longer and more involved config like the one we're writing here with VPNs, it's a good idea to stop after each phase, if you will, and just quickly review your config. Just make sure you're not missing anything, because it's easier to spot something you're missing, say from a policy right here, than when our config is 3 to 4 to 5 times as long, because we got to write 2 policies, a crypto ACL, we got to tie that in, we got to write some pre-shared keys, a couple of other things. So it never hurts to review your config before you're actually finished with the entire thing. So taking a look at router 1's there and router 3's here, just that one little difference in the lifetime, which we know theoretically won't make a difference or won't hurt us. And before we get to the transform sets, though, we do need to create those pre-shared keys. That won't take very long. I apologize, we're a little offline there. There we go. And for our pre-shared keys, what we're going to do is start with crypto ISACMP, and we're going to put the key right there in the middle. Set pre-shared key for remote peer. We definitely want an encrypted password, and I'm going to put CCNA for the password here. And we're going to go with the address, and you do actually have to enter the word address, and it's 172.12.123.3. And while we're at it, we're going to go right over to router 3 because I did not pre-config that. Key 6, CCNA address 172.12.123.1. And when you're using pre-shared keys, that's all there is to it. Now let's take a look at these transform sets. First off, talk about what we're transforming here, what we've got, and then we'll configure them. Now, a transform set, it's kind of a merger. What you're doing is defining both encryption and authentication for IKE Phase 2. You're bringing them together because you're defining the encryption and authentication for any IPsec protected traffic using the following: at least one of these 2 security protocols that we talked about earlier, AH or ESP. You can choose to use both. You also have to choose the algorithm to be used by AH and or ESP, depending on the choices you made for the first bullet point. Now on the screen here, in a moment, I'm going to have the choices for the transform set, and the reason I'm showing them to you on the board first is because I want to really point out that some of these are authentication related, some are encryption related, one's compression related. You'll figure that one out, of course, on your own when you see it. But you won't see these comments in paren at the in iOS help. But this is going to be a little smaller font, but here we go. So it's crypto IPsec transform set is the command. Then I'll be asked to name it, and then I used iOS help to see the options. And we see a couple of AH options there. They're both authentication options, one using MD5 and one using SHA. There's our IP compression algorithm option, and quite a few ESPs here, and these are all encryption. You'll see they're using ciphers that we've talked about before with DES, 3DES, and AES. And we've got another authentication here using MD5, and then you have a null encryption option, a seal cipher, and then finally an ESPN, I knew it, ESP transform using HMAC SHA authentication. Now of those, and I know it's an overwhelming list at first, but hang in there. At first, you can only choose one type of each of the following. If you're choosing AH authentication, you can pick one. ESP encryption, one. ESP authentication, one. And then finally, IP compression, the comp LZS option, there's only one there, so that's all you could choose. And let's bring the lab up here. And we've got our keys in. Now we're going to go ahead and start a transform set. And I want to show you some options before I go too far here and show you that the router will actually prevent you from choosing 2 of any of those options that we saw on the board. Let's go with, first off, conf T. and then crypto IPsec. Now that's the first thing you got to do. Now we're in IPsec land. We're in phase 2, so we need to use the crypto IPsec command, and transform set is what we're going to do. And you're going to give it a name. And there are some of the options, if not all, and of course different routers, different capabilities will have some different choices, but you see the two authentication header choices right at the top, MD5 and SHA. And note, let's say that I chose HMD5. Note for the next option that SHA option is gone. So again, you can only choose one. I want to go back to the board and show you that list one more time. You can choose one authentication type, one ESP encryption type, one ESP authentication type, and of course IP compression. There's only one there to pick. So we're not going to go with here though. We're going to go with ESP, and we're going to use 3 DES for our encryption, and then we'll use SHA for our authentication. So right here, I'm going to go ahead with CCNA ESP 3 DES. And notice now that the list of options got way shorter because I can't pick, ESP AES any longer or ESP DES because I've chosen 3 DES. That eliminates the other two choices. So now I'm going to pick SHA. Also notice, one more thing I wanted to point out here, notice the CR there. So that means this is a legal command in and of itself. So the authentication options are still there, but they're not required. You can just go with only encryption. But I'm going to go with ESP, SHA, HMAC. And then you'll notice you're down to your AH options and your IP compression options because you've already chosen your 2 ESP options. That's what I'm going with. And we drop down into transform set config mode. Let's take a look at our options here, and not very many. You've got default, exit, and no. We're used to those, and there's only one other one, and that's encapsulation mode. This is where you choose tunnel mode or transport mode, and you actually have to put the word mode first and then transport or tunnel. I'm going to go with transport here, and that is it for our transform set. It's one long line with crypto IPsec transform set, then your tag, whatever name you want to give it, and then your choices, encryption and or authentication. And now we need to talk about the lifetime here a little bit of IKE Phase 2 SA, the actual IPsec SA. We're going to do that right now. We're going to go right into it because it's a global command. It's not in your transform set. So if you look for it there, by golly, you will not see it. It's crypto IPsec, and what we want is security association. I didn't have to type all that out, but it's a good tip when you're first learning a command too, just typing it out all the way instead of shortcutting it a little bit or typing half of it in and let the router take it. I like to type the whole thing out when I'm learning a new command. So we've got show association here. A couple of interesting choices here. We're going to go with lifetime, but I want to discuss that idle time with you because I mentioned in a previous video that you could have this SA deleted after it hasn't been used for a while. And you can do that with idle time. And that should look familiar now, except notice it doesn't tell you how many seconds or what unit of time you're using. So it's a good idea to know that that is seconds. I know you have that down by now, and you certainly even have the range 60 to 86,400 in your head. But if you want to go with idle time, you can do it that way. What we're going to do is take a look at the lifetime options, and notice now that we have the option of seconds, which we would expect by this point, but also kilobytes. So if you want to go by a volume-based key duration and say, okay, the lifetime of the SA is after this many kilobytes goes through, you can do that. And your range gets a little bit larger. So you have to do a little math there to figure out exactly what you want, but that's fine if you want to go with the volume. But if you want to go by time, you'll simply go by lifetime right here. Whoops, I already had that part. Let's try seconds. You actually have to type in the word seconds and then 120 to 86,400. And we'll go ahead and go with 86,400 there. So some extra options there for your phase 2 essay, but whether you want to use idle time or you want to tie it down to a certain amount of volume or you want to tie it down to an overall amount of time, you have all three of those options right there. So I believe though we're almost near the end of this config, but we need some kind of traffic to trigger this entire thing. That's our interesting traffic, and we're going to talk about that and define it coming up next. With our IKE policy in place, our IKESA policy in place, both policies written, it's time to put the interesting in interesting traffic with a crypto access list. This is how we define the traffic that's going to trigger the build. Because if we don't, the default is we're not going to have a build. You can have all the policies you want, but if you don't have some kind of interesting traffic defined, that is the traffic that puts the entire VPN build into operation, then it doesn't matter how many policies you got. So, what is a crypto ACL? That sounds complicated, doesn't it? I thought it was going to be really complicated the first time I heard of it. Ooh, crypto ACL. Well, it's a crypto ACL is simply an extended ACL. That's all it is. It's going to be applied very differently than anything you've seen before. And by the way, a crypto ACL has to be an extended ACL. It cannot be a standard, as we'll see live here in a few minutes. Thing is that the purpose of the crypto ACL depends on whether the ACL is being applied to outbound or inbound traffic. These are very important roles. For outbound traffic, a crypto ACL permit indicates traffic that will be protected by IPsec. A crypto ACL deny applied to outbound traffic indicates traffic that will not get IPsec protection, but it will still be transmitted. And I say it like that because it's so easy. Your mind's eye sees a deny. It's like, okay, that traffic's not going out. We know better. The traffic's still going out. It's not being denied transmission. It's being denied IPsec protection. That's what we're talking about here with a crypto ACL. What about inbound traffic? Well, one purpose and one purpose only, and that's a permit statement. A crypto ACL permit indicates traffic that is expected to be IPsec protected upon arrival. If it isn't, then that traffic is dropped. So two wildly different operations going on, right, between outbound and inbound traffic. We're way past the days of just doing permit and deny traffic. Some important rules there, but what might surprise you is that since there's such a big difference between outbound traffic and inbound traffic with a crypto ACL, but you will not be indicating in or out when you apply a crypto ACL as you would with a regular ACL, as in this example. I did have this in Cisco router font, but when you enlarge that, it really just burns the retina. So I've got it in regular font here for you. And you can see I'm on fast Ethernet interface. I wanted to apply access list 101. So I put IP access group 101, and we know that is not by itself a legal command. You've got in and out, and you have to specify which one of those it is. But when we apply an ACL, a crypto ACL, you're not going to do that. This is actually what happens. When an extended ACL is used as a crypto ACL, each line is read forward for outbound traffic and backward for inbound traffic. And I've got this on the board for you. We'll write it on the routers as well. But on router 1, access list 103, permit IP host 172.12.123.1, host 172.12.123.3. Source destination, we know that it's an extended ACL, we know the syntax. Now, when this is part of a crypto map, the ACL, again, it's read forward for outbound traffic, and it defines interesting traffic. And that VPN is going to go up when traffic sourced from 172.12.123.1 is leaving the interface for 172.12.123.3. It's going to trigger the VPN build, and that traffic will be IPsec protected. So far, so good. But when traffic comes back, the ACL on router 1 is read backwards, where the source is 123, the destination is 123.1. And when the traffic comes in, router 1 is saying, okay, that traffic better be IPsec protected, or I'm going to drop it like a rock. So while the ACL we write is just like the extended ACL we've written everywhere else, well, the operation of it and the application of it is a lot different. So what I'll do is write this ACL on router 1, the one we just discussed, and a mirror image, not an exact copy on router 3, where the one on router 3 is going to be permit IP host 172.12.123.3, host 172.12.123.1. So both routers will then be able to build a VPN with that interesting traffic. Now, on this subject, it's not on the board, but I want to give you a quick little dad lecture here. If you are cutting and pasting a config this big, I understand. It's a big config. It's a long configuration. And nothing against cut and paste. I do it all the time myself. But you got to be super careful if you're doing that with VPNs, because you can't take the config from one router and just put an exact copy of it on the other and have things work the way you think they're going to work. Because if we did that with the config we have here, if we took all of router 1's config and dropped it on router 3, we'd have to change the ACL line. We'd have to change the ACL 103. We would have to change the setting on the key. Remember the pre-shared key? That had a peer address in it. And we had some other things in there that we would have to change, and you'd have to change this ACL. You got to watch it, because if you are cutting and pasting, you need a mirror image on the other router, not an exact copy. So personally, I think it's easier just to go over to router 3 and config it from scratch. If you really hate to type, I understand that. But my point is, you tend to let yourself in for more troubleshooting than you should have to do if you're copying a VPN config from one router to the other and then just trying to catch all the little edits that you have to make. Okay? One more warning, and this is from Cisco and from me, and it's something that we're going to do here as far as permit host. Using the permit host statement in your crypto ACL, that's perfectly fine, but you should be very wary of using permit any in an ACL that's going to serve as a crypto ACL, especially, of course, if you're doing any for both source and destination, because two things end up happening, and both of them are bad. If you put permit any for your crypto ACL on outbound traffic, what's going to happen? Everything's triggering the VPN and everything's getting IPsec protected. So you got way too much traffic being encrypted and then decrypted to the destination. A lot of overhead. You don't really want to do that. Now, inbound, you got some bad things happening there, because you could have incoming control traffic, protocol keep alives, etc., arriving unencrypted. And you've got an ACL on the router that says, hey, I expect everything that comes in this interface to be encrypted. Well, that's not going to happen. And boy, you're going to have not only malfunctioning network services, but you're going to end up with some lost adjacencies likely as well. So again, using permit host in your crypto ACL is fine. Be very, very wary, careful, don't do it actually, of using permit any for source and destination in that extended ACL. Those are the rules of the crypto ACL, and coming up next, we are going to configure it and put those rules into action. Having covered the crypto map rules in depth and length, we're going to get to our configuration now. The only thing that I've already written is the ACL. I wrote this on R1 and R3, taking care, of course, to put a mirror image on and not an exact copy, and that's the last time I'm going to mention that for at least a few minutes. So let's bring router 1 up, and now we're going to start applying it and making that ACL into a crypto ACL, if you will, and we do that with the crypto map command. And we got to give it a name, so I'm just going to call it CCNA security. And we got to give it something here as far as the sequence number goes. I'm just going to go with 100 here. So this makes it easy to edit a map later if you want to add something, just like ACL sequence numbers do. And now I'm going to go with IPsec ISAKMP. And that's actually going to be it. And we get a note, really a warning. This new crypto map will remain disabled, that means it's disabled now, until a peer and a valid access list have been configured. So you, the experienced network admin, will not panic when you see this. You've probably seen the thing with login and password on a router just when you're setting the console lines or the VTY lines. And I should say, and you've got 5 lines, of course, by default, 0 through 4. And if you put in login first before password, you get this message about, oh, this is invalid until password is entered. You get it 5 times, and the first time you see it, it can panic you a little bit. But after that, you say, okay, just do the password and you'll be fine. Well, as long as you go ahead and set a peer and refer to a valid access list in your crypto map, it's going to be enabled. You're going to be fine. So how do we do that? We're going to do matches and sets here, and we're going to start with match. And you don't see any ACL value here, do you? There's only one, match address, and this is actually the one we use. And here it's going to ask for the ACL number. So it's not match ACL or match list, it's match address. And also note that the theory that we cannot use standard ACLs for this operation is verified because you don't even see the standard numbers here. You only see the extended list, the two ranges, and of course we could have named it if we had wanted to. So we're going to go with match address 103, and we're going to do a couple of sets here. Set values for encryption, decryption. And we've got a couple to choose from, I think about 7 or 8, yeah, 8 of them. And we're going to go with peer and transform set. That's what we need, because first off, we got to set that peer because the router told us we had to. That's our allowed encryption / decryption peer, and that is going to be 172.12.123.3. And we're also going to set the transform set, and we are going to just call CCNA because that's the only one we wrote. And if we had written multiple transform sets, you just put them in the order that you want them to try to be used, and just keep putting proposal tag, because that's actually what they are really. Transform sets are just proposals. We'll see that in some debugs when we actually put this baby into operation. So we've got our set peer, we have our set transform set, and we are good to go. Or are we? We're at the step people tend to forget, and it's the last step. So you don't want to leave this out, because if you leave this out, nothing's going to happen. We wrote the crypto map, we wrote the ACL, then we wrote the crypto map that made that ACL into a crypto ACL, if you will. Now we have to apply it. And you do apply it to the interface in the exact same way, almost, that you would a regular ACL. You're going to use the crypto map command here, and let me use iOS Help here to illustrate to you that the only option here is the name. Always check these when you're troubleshooting, because it's really easy to leave a letter out, something like that. It's got to be exact. And what do we not expect to see here? We do not expect to see in and out, because we are CCNA security certified and we know the deal with the crypto map and the inbound and outbound rules. So the router's not even going to let us try to apply that inbound or outbound. It is just applied. And that is it. That's the config. You get a little message there, ISOCEMP is on, so you're good to go there. It's a confirmation in this case, actually. You'll always see that after you apply the crypto map to an interface. So we wrote our crypto ACL, we wrote our crypto map, and then we applied the crypto map to the interface, 1, 2, 3. That's it. Now we're going to go on over to router 3. Let's just go over those commands one more time, because we've got the ACL over here already. Just want you to see them in action again. Then the number, and then you need IPsec ISOCEMP. And that's all we're going to do. We're not going to use those options. We'll save those for another day. We got our little message. So the first thing we're going to do is match on an IP address, because that's the only option we have there. And it's 103 on this side as well. I set the peer to 172.12.123.1. I set the transform set to CCNA. Ah, look at that. Transform set with tag CCNA does not exist. I love this. Now, this is the kind of thing that you're going to see on the live equipment that you will not see, say, on an exam question, that kind of thing. But I did leave the transform set off on purpose, and yes, that is my story, and I am sticking to it. Because I want you to see that when you're writing these, if you refer to a transform set that doesn't exist, it's going to tell you right here and there. Now, if you're shown a config on an exam, I don't think they're going to say, hey, by the way, you got this message on the router that the transform set doesn't exist. But that is something to look for when you're troubleshooting as well. So what I am going to do during the break is write the transform set, and it's going to match the one on router 1 exactly. I'm going to apply it to the interface. Those are the only two, and then I'll just apply this to the interface, and we will be ready to test and verify. We'll verify the config at the beginning of the next video, take a look at it on both sides, make sure everything's there we need, and then we're going to start testing our VPN and debugging it as well. I'll see you there. My friends, the moment of truth has come after all this speechifying and theory that we've learned and the new terminology and a lot of configuration. It's time to generate a little bit of interesting traffic here on router 1 and watch our site-to-site VPN come to life. To do that, let's run a debug, crypto IPsec. And then I'm going to send the interesting traffic over, and hopefully we'll see a couple of screens of info here. And there we go, and things look good. And you might look at that and say, how can he tell that things look good? Well, when you see your IPsec essays created here at the very end of the communication of the debug, then you know you're in good shape. And a lot of familiar information there. And here for SA trans, I'm going to go back up to the top of this and we'll just take a quick look through. And we send our ping over. You can see the IPsec SA request information is listed right here, and there's a validate proposal request, which we always like. And we go through there. There's a mention of a crypto map right here and a source address and a destination address. That's good stuff to see. Now note, here's the ping result, and the success rate is 80%. Most of the time when you're building a VPN, that first packet is going to time out, and you might even see the second one time out while it's being built. And we'll see that in one of the show commands we'll run in a moment. When I send a ping over now, which I'll do in just a moment, we should see 100% because, of course, the VPN is already in place. And so, again, some familiar looking information there and configurations, but we go through here and the essays created at the bottom, and we are looking good. Now let's go ahead and send that ping. Actually, let's do the show command first because I want to show you something. No pun intended. Wasn't even a pun. I don't know what you call that, but we'll just move on. You can see with show crypto session, the session status is up and active. Always a good thing. If it were down, we might have an issue. But it's not down. You can see the peer, you can see the port number, you can see the IKE SA information right here. Here's your flow information, and that looks familiar as well. That's our ACL. You've got 2 active essays, and the origin for the IPsec was a crypto map, so we're looking good there. Let's run show crypto ISAKMP SA. And here, idle is actually what we want. We're in something called quick mode right now. We didn't get into the different kind of modes we could set as far as an aggressive mode and a quick mode, but I just kept it at the default. So the state of QM idle is actually what we're looking for here. So again, in good shape there. You see the destination and source there at the beginning. And one more I want to run here, and that's our IPsec SA. Lots more information here, but one thing I really want to point out is that you can see the number of packets encapped, encrypted, and then decapped and decrypted. And notice right now everything's at a 4, because when I sent the ping out, we had 1 send error, and there it is. And then the other 4 packets went out successfully, the echoes came back, so that's why we see all 4s there right now. And I will go ahead and send that ping now. I will go ahead and send that ping now. There it is. And let's go ahead and run show crypto IPsec SA. And you can see now those numbers have gone up to 9. So this is a great command. If you think you're having any kind of issue with encapsulation or de-encapsulation, just watch your incrementation right there. And of course, watch your send errors as well. That is it for our site-to-site VPNs. A lot of information here. Like I said, watch the vids as many times as you need to. Pick up that terminology. There's a lot of configuration here step by step, but when you have that little blueprint in mind for the steps, then you're going to be way ahead of the game. And right now, it is time to move on to another section.